You should not exist. Every atom in your body, every molecule of water, every strand of DNA, the chair beneath you, the air in your lungs, all of it should have collapsed into nothing roughly 1/1000th of a second after forming. Classical physics demands it. The math is airtight. An electron orbiting a nucleus is an accelerating charge, and accelerating charges radiate energy. That electron should spiral inward at catastrophic speed, crash into the nucleus, and erase the atom from existence before it ever had a chance to become anything. And yet, here you are, breathing, thinking, made of trillions upon trillions of atoms that have no right to be stable. This is not a small problem. This is the problem. The kind of paradox that should have stopped physics dead in its tracks the moment Ernest Rutherford split the atom open in 1911 and found a tiny dense nucleus with electrons somehow suspended around it in empty space. For years, no one could explain it. The best minds of the early 20th century stared at this fatal flaw and realized the universe they thought they understood was built on a foundation that could not hold. Then quantum mechanics arrived, not as a patch, not as a workaround, but as a complete rewrite of reality itself. And buried inside that rewrite was an answer so strange, so precise, so utterly unlike anything that came before, that it would become the most accurately tested prediction in the history of science, accurate to 10 significant figures. A number so tight it makes general relativity look like a rough sketch. This is the story of why matter exists, why atoms survive, why there is a world at all. And it starts with a mystery that should have ended everything before it began. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You are made of atoms. Every thought in your head, every breath you take, every word you've ever spoken exists because somewhere in the architecture of reality, atoms hold themselves together long enough for complicated things to happen. Your skin is atoms, your bones are atoms. The device you're holding right now, the photons bouncing off it into your eyes, the electrical signals running through your neurons as you process this sentence, all of it depends on a single absurd fact. Atoms are stable. That shouldn't be true. According to the rules of physics as they were understood a little over a century ago, atoms should not exist for longer than 1/1000th of a second. Not some atoms, not fragile atoms, all atoms, every one of them. The hydrogen in your body, the carbon holding your DNA together, the oxygen you just inhaled, none of it should be here. And yet here you are, breathing it, thinking with it, made entirely of a substance that by all rights should have collapsed into non-existence before the first star ever ignited. This is not a technicality. This is not a footnote in some obscure corner of theoretical physics that only matters to people with advanced degrees and too much time on their hands. This is the foundation underneath everything. If atoms don't work, nothing else gets to happen. No chemistry, no molecules, no water, no rocks, no planets, no stars fusing hydrogen into helium in their cores, no light, no heat, no universe capable of looking at itself and asking why it exists in the first place. The fact that you are sitting here right now, alive and conscious, is direct evidence that something in the classical understanding of matter was catastrophically wrong. And for a brief, terrifying moment in the early 20th century, the smartest people on Earth stared at that wrongness and had absolutely no idea how to fix it. So how does this happen? How does the entire field of physics, built on centuries of careful observation and rigorous math, Look at the atom and realize the thing holding reality together shouldn't be able to hold itself together. The answer starts with what atoms actually are, or at least what we thought they were. An atom is almost entirely empty space. If you scaled one up to the size of a football stadium, the nucleus at the center would be roughly the size of a marble sitting on the 50-yard line. Everything else, the entire volume of the stadium, the seats, the air, the lights overhead, that's where the electrons live. Except they're not distributed evenly. They're not filling the space like a fog. In the classical picture, they're orbiting. Tiny particles with negative electric charge, whipping around a positively charged nucleus at extraordinary speeds, held in place by the electromagnetic attraction between opposite charges. It's a tidy image, elegant even. The atom as a miniature solar system, electrons circling the nucleus the way planets circle the sun. Ernest Rutherford gets credit for that picture, though he'd be the first to tell you it wasn't originally his idea. In 1911, Rutherford and his team at the University of Manchester fired alpha particles, helium nuclei, at a thin sheet of gold foil. Most of the particles passed straight through. A few bounced back at sharp angles, as if they'd hit something solid. Rutherford later said it was as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The only explanation that made sense was that the atom's positive charge wasn't spread out like a cloud. It was concentrated in a tiny dense core at the center, the nucleus. Everything else was empty space with electrons somewhere on the outside. That discovery won Rutherford a Nobel Prize. It also broke physics, because if you take that model seriously, if you actually sit down and work through what the equations say should happen to an electron moving in a circle around a nucleus, the math tells you something deeply uncomfortable. The electron shouldn't stay in orbit. It should radiate all of its energy away in a fraction of a second and spiral directly into the nucleus. The atom should collapse immediately, not over billions of years, not after some slow decay process. Immediately, on a timescale so short that nothing you would recognize as matter could ever have time to exist. Here's why. An electron in orbit is accelerating. That sounds wrong at first, because we usually think of acceleration as speeding up. But in physics, acceleration is any change in velocity. And velocity isn't just speed. It's speed in a particular direction. If you're moving in a straight line at a constant speed, you're not accelerating. But if you're moving in a circle, even at constant speed, your direction is changing every instant. You're accelerating toward the center of the circle. That's what keeps you in the curve, instead of flying off in a straight line. The same applies to electrons. An electron orbiting a nucleus is constantly changing direction. It is constantly accelerating. Now here's the problem. One of the foundational results of classical electromagnetism, worked out in the late 1800s by James Clerk Maxwell and others, is that an accelerating electric charge radiates energy, not under special conditions, not if you push it the right way, always. It's not optional. Accelerate a charge, and it will shed energy in the form of electromagnetic radiation, light, radio waves, whatever frequency the math spits out. This is how antennas work. You shake electrons back and forth in a wire, and they radiate radio waves. This is why synchrotrons, machines that whip particles around in circles at nearly the speed of light, glow so brightly. The particles are accelerating, and they're hemorrhaging energy as a result. Apply that logic to the atom, and the conclusion is unavoidable. The electron is a charged particle. It's accelerating, so it must be radiating, and as it radiates, it loses energy. As it loses energy, it can't maintain its orbital speed. It slows down. The electromagnetic attraction to the nucleus pulls it inward. It spirals closer. The tighter the spiral, the faster it accelerates. The faster it accelerates, the more energy it radiates. The process feeds on itself. The electron doesn't drift gradually into the nucleus over centuries. It screams inward in a runaway cascade, shedding energy faster and faster until it collides with the nucleus and the atom ceases to be an atom. It becomes a tiny dense lump of collapsed charge with no structure, no chemistry, no ability to bond with other atoms or do any of the things atoms need to do to build a universe. How fast does this happen? The calculation isn't even that complicated. If you assume the electron starts in an orbit roughly the size of a hydrogen atom, about 1/10 of a nanometer across, and you apply the equations of classical electromagnetism, the electron loses all of its orbital energy and crashes into the nucleus in about 1/10 billionth of a second. That's 0.1 nanoseconds. For comparison, the time it takes light to travel from one side of a hydrogen atom to the other is about 300 times longer. The collapse happens faster than light can cross the space the electron is supposed to be occupying. This isn't a slow fade. This is instantaneous annihilation. Now scale that up. You're not made of one atom. You're made of roughly 7 octillion of them. A 7 followed by 27 zeros. Every single one of those atoms, if the classical model were correct, should have collapsed within a nanosecond of forming. There is no stable matter. There is no such thing as a molecule. There is no water, no carbon dioxide, no methane, no organic chemistry, no proteins, no DNA, no cell membranes, no neurons, no brains, no thoughts. The universe doesn't get to be complicated because the pieces that would build complicated things don't stick around long enough to assemble. You wind up with a cosmos full of primordial hydrogen and helium gas that never condenses into stars because there are no stable atoms to gravitationally collapse in the first place. Actually, scratch that. You don't even get hydrogen gas. Hydrogen is an atom, one proton, one electron. If the electron can't stay in orbit, hydrogen doesn't exist. What you're left with is a thin soup of free protons and free electrons drifting through an empty expanding void, incapable of interacting in any way that produces structure. That is the prediction. That is what the equations say, and the equations worked everywhere else. Maxwell's electromagnetism explained light, radio waves, the behavior of circuits, the operation of generators and motors. It was one of the towering achievements of 19th century science, and it was tested to extraordinary precision. The theory wasn't wrong, or if it was, nobody could point to where the error was. So what do you do when your best theory of matter predicts that matter shouldn't exist, and yet you are sitting in a laboratory made of matter, holding instruments made of matter, breathing air made of matter, staring at experimental results that very clearly show atoms are not collapsing? You can't ignore the problem. You can't pretend the math doesn't say what it says. And you can't exactly throw out electromagnetism because it works for everything else. For a while, people tried to patch it. Maybe the electron isn't really orbiting. Maybe it's sitting still somehow, embedded in the nucleus. That doesn't work. If the electron and the nucleus occupy the same space, the atom has no size, and we know atoms have size because we can measure it. We can see them now with scanning tunneling microscopes. We can watch them bond into molecules. We can measure the spacing between atoms in a crystal lattice. The atom is not a point, so the electron has to be somewhere outside the nucleus. Maybe the electron is orbiting, but something damps the radiation. Maybe the nucleus has some kind of stabilizing field that cancels out the energy loss. Nobody could explain what that field would be or why it would exist. and every attempt to model it mathematically either violated other known laws of physics or predicted effects that didn't show up in experiments. By the early 1900s, the situation was dire. You had one set of experiments showing atoms were real, stable, and structured like tiny solar systems. And you had another set of equations, rock-solid equations, saying those solar systems should evaporate before you could blink. Both couldn't be true, and yet both were staring physicists in the face every time they walked into a lab. This is what a crisis in physics looks like. Not a minor discrepancy where one measurement is off by a few percent and everyone argues about error bars. A full existential breakdown where the theory says reality is impossible and reality goes ahead and exists anyway. The response from the physics community was about what you'd expect. Some ignored it and worked on other problems. Some assumed someone smarter would figure it out eventually. And a small number of people, the ones who couldn't let it go, started looking for an explanation that didn't require throwing out everything that had been learned in the previous 2 centuries. They didn't know it yet, but the answer wasn't going to come from fixing the old rules. It was going to come from realizing the rules themselves only applied to a universe much larger and much slower than the one inside an atom. At the scale of the electron, reality worked differently, not slightly differently. Fundamentally differently, in ways that would force physicists to rethink what they meant by position, momentum, energy, and eventually existence itself. There's a reason this chapter is called The Ghost in the Machine, because that's what the electron was in the classical picture. A ghost, something that should be there, something the experiment said was there, but something the theory insisted couldn't stay there. A particle with charge and mass and speed, orbiting a nucleus, holding your body together, and yet, according to the best understanding of the time, vanishing into nothing faster than the time it takes light to travel the width of a single atom. The fact that you're still here, that atoms didn't collapse the moment they formed, that the universe went ahead and built stars and planets and eventually people capable of noticing the problem, is proof that somewhere in the machinery of reality there was a piece no one had seen yet, a rule no one had written down, a way for the electron to stay in orbit without radiating, without spiraling, without destroying the atom it was supposed to be part of. That rule exists. We know what it is now. It's called quantum mechanics, and it didn't just solve the problem of the collapsing atom. It redefined what we mean by particles, waves, certainty, and measurement. It turned out the electron wasn't orbiting at all, at least not in the way Rutherford imagined. It wasn't a tiny ball whipping around a nucleus like a planet around a star. It was something stranger, something that doesn't have a single definite position until you force it to. Something that exists as a spread-out cloud of probability, a wave of potential locations, and only collapses into a point when you interact with it. In that picture, the electron doesn't accelerate in the classical sense. It doesn't have a trajectory. It doesn't radiate because it's not moving the way moving is defined in Newtonian mechanics. It's sitting in a quantum state, a solution to an equation that describes where it's allowed to be and where it isn't. And those allowed states, those orbits that aren't really orbits, are stable. They don't decay, they don't radiate. The electron stays where it is because the math says that's the only place it can be. But that explanation didn't come easily. It took decades of confusion, bitter arguments, experimental surprises, and a willingness to accept that the universe at its smallest scales was genuinely weird in ways no one had anticipated. The people who figured it out didn't start by trying to save the atom. They started by trying to explain completely different problems: black body radiation, the photoelectric effect, the spectrum of hydrogen. And piece by piece, experiment by experiment, they stumbled into a new framework that made the impossible possible. The atom shouldn't exist. The fact that it does is the single most important clue that classical physics, for all its elegance and precision, was incomplete. There was a deeper layer underneath, a place where particles weren't particles in the way we thought, where certainty gave way to probability, and where the rules governing matter were written in a language no one had learned to speak yet. The classical atom was a beautiful idea. It just happened to be wrong. And figuring out why it was wrong, what was really happening inside that impossibly tiny space between the nucleus and the outer edge of the electron's presence, turned into one of the great intellectual adventures in human history. An adventure that didn't just explain why atoms hold together. It explained why matter exists at all, why chemistry works, why the periodic table has the structure it does, why stars burn, why you can hold a cup of water without it evaporating into a cloud of free protons and electrons. The ghost in the machine wasn't a ghost, it was real, but it was playing by rules no one had written down yet. And the moment physicists started writing those rules, the universe stopped being the place they thought it was and became something far stranger and far more interesting. What those rules were, how they were discovered, and why they turned out to be the most accurate description of reality ever tested by experiment, that's the rest of the story. The problem with revolutionary discoveries is that nobody plans them. They happen by accident, or by stubbornness, or because someone ran an experiment expecting one result and got something completely different. Ernest Rutherford was not looking for the nucleus when he found it. He was not trying to overturn the accepted model of the atom. He was running a fairly routine experiment on how alpha particles scatter when you fire them through thin materials, and the results came back wrong. Not slightly wrong, catastrophically, impossibly wrong. The kind of wrong that makes you check your equipment 3 times, recalculate everything, and then sit in your office staring at the wall because the numbers are telling you something that shouldn't be true. Rutherford was born in 1871 in rural New Zealand, the 4th of 12 children in a family that made its living farming flax. He was bright, competitive, and relentlessly practical. He won a scholarship to Canterbury College in Christchurch, then another to Cambridge, where he arrived in 1895 to work under J.J. Thomson at the Cavendish Laboratory. Thomson had just discovered the electron 2 years earlier, though he called it a corpuscle at the time, and the Cavendish was the center of the new physics of electricity and radioactivity. Rutherford fit in immediately. He had a gift for designing clever experiments and an even rarer gift for knowing which results mattered. Within a few years, he had identified 2 distinct types of radiation emitted by radioactive materials. He called them alpha and beta, names that stuck. By 1907, he was a professor at the University of Manchester, running his own lab and widely regarded as one of the best experimental physicists alive. The atom at that point was still a mystery. Everyone agreed atoms existed. Chemistry had proven that much. Elements combined in fixed ratios, compounds had predictable properties. Gases behaved according to laws that only made sense if matter was made of discrete particles. But what those particles looked like inside, what held them together, how they were structured, that was open territory. The most popular model in the early 1900s was J.J. Thomson's. Thomson had discovered the electron, so people listened when he proposed a picture of the atom. He imagined it as a sphere of positive charge with electrons embedded inside like raisins in a pudding. The positive charge was spread out evenly through the whole volume of the atom. The electrons, tiny and negatively charged, floated in that positive soup, held in place by the attraction between opposite charges. The atom was electrically neutral overall because the total negative charge of the electrons balanced the total positive charge of the pudding. It was a tidy image, stable, symmetrical, easy to visualize. People called it the plum pudding model, and for a while it was the best explanation anyone had. Rutherford was not convinced. He did not have a better model yet, but something about the pudding picture felt wrong to him. Atoms were solid. You could stack them into crystals. You could measure their size. If the positive charge was spread out like a diffuse cloud, it was hard to see why atoms would have sharp boundaries or why they would resist being compressed. He did not say this loudly. He just kept running experiments. In 1909, he assigned two of his researchers, Hans Geiger and Ernest Marsden, to study how alpha particles behave when you fire them at thin metal foils. Alpha particles were known to be positively charged and relatively heavy, about 4 times the mass of a hydrogen atom. Rutherford had spent years studying them. If you wanted to probe the inside of an atom, alpha particles were a good tool. They were fast, energetic, and small enough to get close to whatever structure was hiding inside. The setup was straightforward. You take a source of alpha particles, typically a small sample of radioactive material like radium. You aim the particles at a very thin sheet of metal foil. Gold worked well because you could hammer it into foils only a few hundred atoms thick. Then you put a detector on the other side and measure where the particles end up after passing through. If Thomson's model was correct, the alpha particles should pass through with only minor deflections. The positive charge in the atom was spread out. The electrons were far too light to deflect a heavy alpha particle by any significant amount. You would expect the particles to plow straight through the pudding, maybe jostled slightly, like a cannonball passing through fog. That was the prediction. Geiger and Marsden set up the apparatus and started collecting data. Most of the alpha particles did exactly what they were supposed to. They went straight through the gold foil and hit the detector on the far side, barely deflected at all. But a few did something strange. A small number, maybe 1 in 8,000, bounced back at sharp angles. Some deflected by 90 degrees. A handful came almost straight back toward the source, as if they had hit something solid and rebounded. Geiger brought the results to Rutherford. Rutherford did not believe them. He told Geiger to check the equipment. Geiger checked. The results held. Rutherford later said it was the most incredible event of his life. He described it as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. There was no way to explain that result with the plum pudding model. A diffuse cloud of positive charge spread over the entire volume of an atom could not exert enough force to reverse the direction of a fast-moving alpha particle. You would need something much smaller, much denser, something with enough concentrated positive charge to repel the alpha particle hard enough to send it flying backward. Rutherford sat with the data for months. He ran the calculations over and over. The math was unambiguous. The only way to produce the scattering pattern Geiger and Marsden had observed was if the atom's positive charge was not spread out at all. It had to be concentrated in a tiny region at the center. Rutherford estimated the size of that central core by working backward from the scattering angles. The result was shocking. The nucleus, as he eventually called it, was about 10,000 times smaller in radius than the atom itself. If you scaled an atom up to the size of a large sports stadium, the nucleus would be smaller than a marble sitting in the middle of the field. Everything else was empty space. He presented the findings in March 1911 at a meeting of the Manchester Literary and Philosophical Society. The paper was published 2 months later in Philosophical Magazine under the title The Scattering of Alpha and Beta Particles by Matter and the Structure of the Atom. It was not a flashy title, the content was explosive. Rutherford proposed that the atom consisted of a tiny, dense, positively charged nucleus containing nearly all of the atom's mass, with electrons orbiting that nucleus at relatively vast distances. The model looked like a miniature solar system, nucleus at the center, electrons circling on the outside, held in their orbits by the electromagnetic attraction between opposite charges. The atom was mostly empty, with all the action happening at two extremes, the incredibly dense nucleus and the incredibly light electrons moving somewhere far away in the surrounding space. The model explained the scattering results perfectly. When an alpha particle passed through a gold foil, it mostly traveled through empty space and went straight through. But occasionally, by chance, an alpha particle passed very close to a nucleus. When that happened, the positive charge of the nucleus and the positive charge of the alpha particle repelled each other with tremendous force. The closer the approach, the stronger the repulsion. A head-on collision, or near enough, could reverse the alpha particle's direction completely. The scattering pattern was exactly what you would expect if the positive charge of the atom was concentrated in a region far smaller than the atom itself. Thomson's pudding was gone. Rutherford's nucleus was in. The physics community accepted the result quickly. The experimental evidence was too clean to argue with. Within a few years, the planetary model of the atom was the standard picture in textbooks. Rutherford became one of the most famous scientists in the world. In 1908, he had already won a Nobel Prize for his work on radioactivity, though the committee gave it to him in chemistry rather than physics, a fact that annoyed him for years. The nucleus discovery cemented his reputation. He was knighted in 1914. By the time he died in 1937, he was widely regarded as one of the greatest experimental physicists who had ever lived. His lab at Manchester and later at Cambridge trained an entire generation of physicists who went on to shape the field for the next half-century. But there was a problem. The planetary model worked beautifully as a description of what atoms looked like. It did not work at all as an explanation of why atoms were stable. The moment you took Rutherford's model seriously and applied the known laws of physics to it, the whole thing fell apart. An electron orbiting a nucleus is a charged particle in constant acceleration. And according to classical electromagnetism, an accelerating charge radiates energy. Not sometimes, not under special conditions, always. The electron should lose energy continuously as it orbits. As it loses energy, it should spiral inward. The tighter the spiral, the faster it accelerates. The faster it accelerates, the more energy it radiates. The process runs away with itself. In a fraction of a nanosecond, the electron crashes into the nucleus and the atom collapses. Rutherford knew this. Everyone working in the field knew this. The equations were not controversial. Maxwell's theory of electromagnetism was one of the most successful theories in the history of physics. It explained the behavior of light, radio waves, electric circuits, magnets, every electromagnetic phenomenon anyone had ever tested. The math said that an orbiting electron should radiate, and there was no classical mechanism to stop it. The planetary model was descriptively accurate. It matched the scattering experiments. It explained the structure Rutherford had observed, but it was not dynamically stable. It could not last. And yet, atoms did last. They lasted for billions of years. Hydrogen atoms formed in the first few minutes after the Big Bang were still around. The carbon atoms in your body had been cycling through stars and planets and living things for billions of years without collapsing. Something was wrong. Some physicists hoped there might be a way to patch the model without abandoning classical physics entirely. Maybe the electron was not really accelerating. Maybe it was locked into a stationary state somehow, suspended in the electromagnetic field of the nucleus without actually moving. That did not work. If the electron was not moving, it had no kinetic energy. The electromagnetic attraction to the nucleus would pull it straight in. The electron had to be moving to stay in orbit, the same way a satellite has to be moving to stay in orbit around Earth. Sitting still was not an option. Maybe the nucleus emitted some kind of stabilizing field that cancelled out the radiation. Nobody could specify what that field would be or how it would work, and every attempt to model it mathematically either violated conservation of energy or predicted effects that did not show up in experiments. Maybe the atom was not a planetary system at all. Maybe the electrons were embedded in the nucleus somehow, the way Thomson had originally suggested, just with the positive charge concentrated rather than spread out. That did not work either. If the electrons and the nucleus occupied the same space, the atom would have no size. And atoms did have size. You could measure it. You could see the spacing between atoms in crystals using X-ray diffraction. You could measure the distances between atoms in molecules using spectroscopy. The electron had to be somewhere outside the nucleus. There was no way around it. But if the electron was outside, it was orbiting. And if it was orbiting, it was accelerating. And if it was accelerating, it was radiating. And if it was radiating, the atom was doomed. For a few years, the situation was genuinely uncomfortable. Rutherford had cracked open the atom and shown what was inside, and what was inside made no sense. The nucleus was real. The scattering experiments proved it. The empty space around the nucleus was real. The structure of the atom was no longer in doubt. But the mechanism holding that structure together was completely missing. Classical physics could describe the atom, it could not explain it. The rules that worked everywhere else did not work here, and nobody knew why. Rutherford himself was not particularly bothered by the instability problem. He was an experimentalist. His job was to measure things and report what he found. If the theorists could not explain his results, that was their problem. He kept running experiments, but the theorists were bothered, deeply bothered. The atom was not some exotic corner case. It was the foundation of everything. If you could not explain why atoms held together, you could not explain chemistry. You could not explain why matter was stable. You could not explain why the universe looked the way it did. The planetary model was also producing another problem that had nothing to do with stability. Atoms emitted light. That had been known for decades. Heat up a gas and it glows. Pass an electric current through it and it glows. The light was not random. Every element emitted a unique set of specific colors, a spectrum. Hydrogen emitted red, cyan, and violet lines at very precise wavelengths. Sodium emitted a characteristic yellow doublet. Helium had its own pattern. You could identify an element just by looking at the light it gave off. Spectroscopy had become one of the most powerful tools in chemistry and astronomy. But nobody knew why the spectra looked the way they did. Why specific wavelengths? Why those wavelengths and not others? In the planetary model, an electron orbiting a nucleus should be able to emit light at any wavelength, depending on how fast it was moving and how tightly it was orbiting. You should get a continuous spectrum, a smooth rainbow. You did not. You got sharp, discrete lines. The electron was clearly picking certain specific energies and ignoring everything in between. Classical physics had no explanation for that either. So by 1911, the atom had gone from a solved problem to a broken one. Rutherford had given physicists the structure, a nucleus surrounded by orbiting electrons. That part was settled, but the dynamics, the explanation of why that structure was stable and why it behaved the way it did, that was completely missing. The tools that had worked for everything else, Newtonian mechanics, Maxwell's electromagnetism, the accumulated knowledge of 2 centuries of classical physics, all of it stopped working when you zoomed in past a certain scale. The atom was too small, too fast, too strange. The rules at that scale were different. Nobody knew what the new rules were. Nobody even knew how to start looking for them. The ghost in the machine was real. The planetary model had made that clear. But the ghost was not playing by the rules anyone had written down. It was doing something else, something that did not fit into the framework of classical physics at all. And until someone figured out what that something was, the atom would remain an open wound in the middle of physics, observed, measured, described, but fundamentally unexplained. Rutherford's revelation was not the end of the story. It was the beginning of a much stranger one. The atom had a nucleus. The nucleus was tiny and dense. The electrons were somewhere outside, orbiting in empty space. That much was clear. What was not clear was how any of it stayed together long enough for you to exist. The answer to that question would come from a direction nobody expected, not from experiments on alpha particles or scattering angles or nuclear collisions. It would come from trying to understand light, from staring at the spectrum of hydrogen and realizing that the electron was not where you thought it was. It was not moving the way you thought it was, and the rules governing its behavior were written in a language that had not been invented yet. A language that would force physicists to give up the idea of definite positions, definite speeds, and definite trajectories entirely. The electron was not a particle orbiting a nucleus. It was something else, something that existed in more than one place until you looked at it. Something that did not have a path until you forced it to. Something that lived in a cloud of probability rather than a point in space. That realization, when it finally came, would explain why the atom did not collapse. It would explain the discrete spectra. It would explain stability, chemistry, the periodic table, the existence of matter itself. But it would also break every intuition anyone had ever had about what it meant for something to exist. And the man who started that process was not thinking about atoms at all. He was thinking about why hot objects glow. The answer came from the wrong place. It came from a man who was not trying to save the atom. He was not thinking about electrons or nuclei or the stability of matter. He was thinking about ovens. Specifically, he was thinking about why hot objects glow the way they do, and why the equation everyone was using to describe that glow kept predicting that the universe should be on fire. Max Planck did not look like a revolutionary. Born in 1858 in Kiel, Germany, he was the model of academic respectability, conservative, methodical, deeply traditional in his approach to physics. He wore three-piece suits. He played piano. He loved classical music. His colleagues described him as cautious, even timid. He spent the first half of his career working on thermodynamics, the physics of heat and energy, and he did it well enough to earn a professorship at the University of Berlin in 1889. But he was not flashy. He did not chase grand theories. He worked on practical problems, the kind that required patience and careful calculation. And in 1894, he was handed a problem that had been annoying physicists for years, a problem about light, heat, and the bizarre behavior of glowing objects. The problem was called black body radiation. A black body is an idealized object that absorbs all the light that hits it and emits light based purely on its temperature. No object in nature is a perfect black body, but many things come close. A chunk of iron heated in a forge, the filament of an incandescent bulb, the walls of an oven. Heat them up and they glow. The hotter they get, the brighter they glow, and the color shifts. Red at lower temperatures, orange, yellow, white at higher temperatures. Physicists had been studying this for decades because it seemed like a straightforward problem. You heat something up, it radiates energy. Write down the equations, solve for the spectrum of light it should emit, and you are done. Except the equations did not work. Classical physics predicted that as you moved toward shorter wavelengths, toward the blue and ultraviolet end of the spectrum, the amount of energy radiated should keep increasing, not gradually, explosively. The formula said that a hot object should emit infinite energy at infinitely short wavelengths. That result had a name. Physicists called it the ultraviolet catastrophe. It was not a small error. It was not a rounding mistake. It was a prediction that every object with any temperature above absolute zero should be pumping out infinite amounts of ultraviolet and X-ray radiation. Your body is warm. You should be glowing like a star. The chair you are sitting on should be drowning you in high-energy photons. The walls of your room should be lethal. Obviously, that does not happen. Warm objects do not incinerate everything around them. The prediction was absurd. But the math that led to the prediction was solid. It came straight from classical thermodynamics and Maxwell's equations. There was no obvious place where the logic broke down. Planck was hired by a German industrial consortium to figure out how to build better light bulbs. The companies wanted more efficient lighting, and efficiency depended on understanding exactly how heated filaments radiated energy. So Planck sat down with the experimental data and tried to fit an equation to it. The data itself was clean. Physicists had measured the spectra of blackbody radiation with great precision. The curves were smooth, predictable, and completely inconsistent with what the classical equations said should happen. At short wavelengths, the intensity did not shoot off to infinity. It dropped. The curve peaked at a wavelength that depended on temperature, and then it fell off smoothly on both sides. Hot objects glowed, but they did not emit infinite energy. They emitted finite, measurable amounts, distributed across a specific range of wavelengths. Planck tried everything. He adjusted the equations. He tweaked the assumptions. He ran the numbers over and over, trying to find a formula that matched the data without violating the principles of classical physics. Nothing worked. Then, in a fit of frustration, he tried something that made no physical sense. He assumed that the energy radiated by the hot object was not continuous. He assumed it came in discrete chunks, little packets of energy that could only be emitted or absorbed in fixed amounts. He did not believe this was real. He thought it was a mathematical trick, a way to make the equations behave. But when he plugged the idea into his calculations, the formula worked perfectly. The curve matched the data. The ultraviolet catastrophe vanished. The energy did not blow up at short wavelengths because the packets of energy got larger at shorter wavelengths, and at some point the object did not have enough thermal energy to emit even a single packet. The radiation cut off naturally. He presented the result in December 1900 at a meeting of the German Physical Society in Berlin. The equation he derived is now one of the most important in physics. The energy of each packet, he said, was proportional to the frequency of the light. Higher frequency light, shorter wavelengths, came in bigger chunks. Lower frequency light, longer wavelengths, came in smaller chunks. The proportionality constant, the number linking energy and frequency, was tiny, absurdly tiny, 6.6 times 10 to the negative 34 joule seconds. He called it H. We call it Planck's constant, and it is now one of the fundamental constants of nature, right up there with the speed of light and the gravitational constant. As of 2018, it is the exact defined value that anchors the kilogram in the international system of units. Planck did not know any of that in 1900. He thought H was an arbitrary fitting parameter, a number you plug into an equation to make it work. He spent the next several years trying to get rid of it, trying to derive the blackbody formula without assuming energy came in chunks. He failed. Every attempt led back to the same conclusion. Energy was quantized. Nobody paid much attention at first. Planck's equation worked, so people used it. But the idea that energy was fundamentally grainy, that it could not be divided into arbitrarily small pieces, struck most physicists as bizarre. Energy was supposed to be continuous. You could have any amount of it. You could add a little more, take a little away. The idea that there was a smallest possible unit of energy, and that trying to emit or absorb anything smaller simply did not happen, felt wrong. It was useful, sure, but useful did not mean real. For the first few years, Planck's constant was treated as a curiosity, a trick that made the math work, not a window into the actual structure of reality. Then Albert Einstein picked it up. In 1905, the same year he published his papers on special relativity and Brownian motion, Einstein wrote a paper on the photoelectric effect. Shine light on a metal surface and it kicks out electrons. Classical physics said the energy of the ejected electrons should depend on the intensity of the light. Brighter light, more energy. That is not what happened. The energy of the electrons depended on the frequency of the light. Blue light kicked out high-energy electrons. Red light kicked out low-energy electrons. Dim blue light and bright red light could have the same intensity, but the blue light always won. Einstein explained it by taking Planck's idea seriously. He said light itself was quantized, not just the way objects emit or absorb energy. The light traveling through space was made of discrete packets, particles of light. He called them quanta. We call them photons. Each photon carried an amount of energy equal to Planck's constant times its frequency. When a photon hit an electron in the metal, it delivered that energy in one lump. If the energy was high enough, the electron escaped. If not, nothing happened. Intensity did not matter because adding more photons did not make each individual photon stronger. You just got more packets of the same size. Einstein won the Nobel Prize for that paper, not for relativity, for the photoelectric effect. The Nobel Committee was still not sure about relativity in 1921. But the photoelectric effect was solid experimental physics, and it confirmed that Planck's constant was not just a fitting trick, it was real. Energy was quantized, and if energy was quantized, then the rules of classical physics, which assumed energy could be divided infinitely, were incomplete. There was a new layer underneath, a graininess to reality that no one had suspected. That graininess only showed up at very small scales, which is why no one had noticed it before. But once you knew to look for it, it was everywhere, and it was about to solve the problem of the collapsing atom. Niels Bohr arrived at the problem in 1912. He was 26 years old, Danish, and had just finished his PhD at the University of Copenhagen. His dissertation was on the electron theory of metals, and it was fine but not groundbreaking. He wanted to work with J.J. Thomson at Cambridge, so he moved to England and showed up at the Cavendish laboratory with a copy of his thesis and a long list of questions. Thomson was polite but not particularly interested. Bohr's English was shaky, and his theoretical approach did not mesh well with Thomson's style. After a few awkward months, Bohr moved to Manchester to work with Rutherford. That turned out to be the right move. Rutherford was an experimentalist, not a theorist, and he had no patience for abstract mathematical arguments. But he respected clarity, and he respected anyone who could explain his results better than he could. Bohr could do that. He looked at Rutherford's nuclear atom, the tiny dense nucleus with electrons orbiting in empty space, and he saw immediately what the problem was. The atom should collapse. Classical electromagnetism said so. The electron should radiate, lose energy, spiral inward and crash. It did not. So classical electromagnetism had to be wrong, or incomplete, or limited in some way no one had figured out yet. Bohr spent months thinking about it. He read Planck, he read Einstein, he read everything he could find on quantization and the new ideas bubbling up around energy and light. And in early 1913, he had an idea. What if the electron could only occupy certain specific orbits? Not any orbit, not a continuous range of distances from the nucleus, only particular orbits at particular energies. In those allowed orbits, the electron would not radiate. It would just sit there, stable, not accelerating in the classical sense. The atom would not collapse because the electron could not spiral inward smoothly. There was no smooth path, there were only discrete steps. The electron was either in one allowed orbit or another, nothing in between. It was a radical proposal. It threw out a huge chunk of classical mechanics. Bohr was saying that the electron did not follow the normal rules of motion when it was bound to an atom. It could not have any arbitrary energy. It could only have specific quantized energies determined by some rule Bohr had not fully worked out yet. And when the electron jumped from one allowed orbit to another, it did so without passing through the space in between. One moment it was in a high-energy orbit. The next moment it was in a low-energy orbit. No smooth transition, no continuous path, just a jump. Bohr called it a quantum leap, and the name stuck. In everyday language, a quantum leap means a big sudden change. In physics, it means something much stranger. It means a change that happens without a middle. An electron changes state, and there is no story you can tell about how it got from one state to the other because it did not travel through the intermediate space. It just appeared in the new orbit, as if the old orbit stopped existing and the new one started. Bohr still needed a rule to determine which orbits were allowed. He found it by working backward from the hydrogen spectrum. Hydrogen was the simplest atom. One proton, one electron. Its spectrum had been measured with extraordinary precision for decades. 4 visible lines, red, cyan, blue, violet, exact wavelengths, no variation. A Swiss schoolteacher named Johann Balmer had found an empirical formula in 1885 that fit the wavelengths perfectly, but it was just a pattern. Nobody knew why the formula worked. Bohr realized that if his allowed orbits were real, the hydrogen spectrum was a direct map of the energy levels. Each line corresponded to an electron jumping from one orbit to another. The energy difference between the two orbits determined the wavelength of the emitted light. Planck's constant linked the two. The energy of the photon was Planck's constant times the frequency of the light. Frequency and wavelength are inversely related, so once you knew the wavelength, you knew the energy. Work backward from the observed spectrum, and you could calculate the allowed energy levels. Bohr did exactly that. He derived a formula for the energy of each orbit based on the principle that the angular momentum of the electron, a measure of its rotational motion, was quantized in units of Planck's constant divided by 2 pi. That single assumption, combined with the classical equations for electromagnetism and circular motion, gave him the energy levels. Plug them into the formula for photon emission, and out came the Balmer series, exact match. The hydrogen spectrum was not a mystery anymore. It was a direct consequence of quantized orbits. Bohr published the model in 3 parts in the summer of 1913 in Philosophical Magazine. The response was mixed. Some physicists loved it. It solved the stability problem. It explained the hydrogen spectrum. It introduced quantization into atomic structure in a way that actually worked. Others hated it. It was a patchwork. It mixed classical mechanics and quantum rules without any clear principle for when one applied and when the other took over. The electron obeyed classical laws while it sat in an orbit, but then it violated those same laws when it jumped between orbits. There was no mechanism, no explanation for why the jumps happened or how the electron decided when to jump. Bohr just said it did, and the math worked. Einstein called it a revelation. He also said it was incomplete and probably wrong in some deeper sense. Rutherford supported it because it fit his nuclear model and because Bohr had worked out the details Rutherford himself could not. But even Rutherford admitted the model felt like a temporary fix, something that worked for now but would not last. Bohr's model had one other feature that bothered people: the quantum leap itself. If an electron jumped from one orbit to another without passing through the space in between, what did that mean? Where was the electron during the jump? Was there a moment when it was nowhere? Or was it in both places at once? Or was the whole idea of asking where the electron was during the jump a category error, like asking what the smell of the color blue is? Bohr did not answer. He could not answer. The math did not describe the transition. It only described the initial state, the final state, and the energy difference between them. The leap itself was outside the model. It was a gap, a place where the equations stopped, and that gap would turn out to be one of the central mysteries of quantum mechanics. The model worked brilliantly for hydrogen. Every line in the hydrogen spectrum, not just the visible ones but the ultraviolet and infrared series as well, fell out of Bohr's equations with precision. It was one of the great triumphs of early 20th century physics. For the first time, someone had taken the structure of the atom seriously, applied a quantum rule, and gotten exact experimental agreement. But the model failed almost immediately when you tried to extend it. Helium has 2 electrons. Bohr's model could not handle it. The math got too complicated. You could not solve the equations. Lithium, 3 electrons, worse. Anything beyond hydrogen, and the model stopped working. You could patch it. You could add extra rules, extra quantum numbers, restrictions on which orbits the electrons could occupy based on their energy and angular momentum and magnetic properties. Those patches worked up to a point. They explained some features of multi-electron spectra, but they were clearly ad hoc, band-aids covering holes in the theory. Bohr knew it. Everyone knew it. The model was incomplete. There was also something deeply unsatisfying about the way the model treated the electron. It was still a particle, a tiny ball, with charge and mass, moving in a definite orbit with a definite speed, except when it jumped, at which point it stopped being a particle moving on a trajectory and became something else. Something that could vanish from one place and appear in another without crossing the space between. That duality, particle when it is sitting still in an orbit, not a particle when it moves between orbits, felt wrong. It felt like the model was hiding something, like there was a deeper structure underneath that Bohr had not yet uncovered. But for all its flaws, the Bohr model changed everything. It proved that quantum rules applied to matter, not just to light. It showed that atoms had internal structure, and that structure was determined by quantization. It explained why atoms emitted discrete spectra instead of continuous rainbows, and most importantly, it solved the stability problem. Atoms did not collapse because the electron could not spiral inward smoothly. It could only jump between allowed orbits, and the lowest orbit was stable. There was nowhere lower for the electron to go. It sat in the ground state, the orbit with the lowest possible energy, and it stayed there unless something gave it enough energy to jump to a higher level. No radiation, no spiral, no collapse. The atom was stable because the rules of classical physics did not apply at that scale. The rules were quantum. And once you accepted that, the universe made sense again. Bohr won the Nobel Prize in 1922. The model that earned him the prize was already outdated. By that point, physicists knew it was not the final answer, but it was the right kind of wrong. It pointed in the right direction. It introduced the idea that electrons in atoms lived in discrete energy levels, that they could transition between those levels by emitting or absorbing photons, that the structure of matter was fundamentally quantum, and it forced everyone to take quantization seriously, not as a mathematical trick, but as a real feature of nature. Planck had quantized energy to solve a problem with ovens. Einstein had quantized light to explain the photoelectric effect. Bohr quantized the atom to stop it from collapsing, and each step made it clearer that classical physics, for all its elegance and success, was only an approximation, a description of reality that worked at large scales and slow speeds, but broke down when you zoomed in far enough. The quantum leap became one of the most famous ideas in physics, and also one of the most misunderstood. In popular language, it means a huge jump, a dramatic change. In physics, it means something subtler and stranger. It means a change that happens in steps, not smoothly. It means the electron does not glide from one state to another. It switches, and during the switch, the usual rules do not apply. There is no trajectory, no path, no story you can tell about the electron's journey from the old orbit to the new one. The electron is in one state, then it is in another state. The transition itself is not part of the picture. It is outside the model, a gap in the narrative, and that gap, that inability to describe what happens during the jump, would haunt quantum mechanics for decades. Some researchers in the 21st century managed to observe the jump in progress using extremely sensitive measurements on individual atoms. The result was surprising. The jump was not instantaneous. It unfolded over a few microseconds, and during that time, the atom was in a superposition, a mixture of both states. The electron was not in the old orbit or the new orbit. It was in both, until the transition completed and it settled into the final state. That observation did not make the jump less strange. It made it more strange because it confirmed what quantum mechanics had been saying all along. The electron does not have a definite state during the transition. It exists in a blur, a cloud of possibilities, until something forces it to pick one. Bohr's model was a bridge. It connected the classical world, the world of particles and orbits and definite trajectories, to the quantum world, the world of probabilities and superpositions and uncertainty. The bridge was shaky. It was built from mismatched parts, classical mechanics on one side, quantum rules on the other, held together with assumptions that did not quite fit. But it worked well enough to get people across. And once they were on the other side, they started building a new framework, a fully quantum description of the atom that did not need to borrow from classical physics at all. That framework would come from Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and a generation of physicists who took the strange implications of quantization and pushed them to their logical conclusion. The electron was not a particle orbiting a nucleus. It was a wave, or it was a cloud, or it was a solution to an equation that described where it might be if you looked. The definite orbit was gone. The definite position was gone. What replaced it was something far stranger and far more accurate. A picture of the atom that did not just explain stability, it explained everything. Bohr's model worked. That was the problem. It explained the hydrogen spectrum with uncanny precision. It predicted the wavelengths of light emitted by excited hydrogen atoms down to the angstrom. It solved the stability crisis by simply declaring that electrons could only occupy certain orbits and could not spiral inward. For a few years, physicists used it, taught it, and quietly pretended not to notice the glaring conceptual holes underneath. The model was half classical, half quantum, stitched together with rules that had no deeper justification. Electrons obeyed Newton's laws while sitting in an orbit, then abruptly stopped obeying them when they jumped between orbits. The jumps themselves had no mechanism. The electron was in one place, then it was in another place, and the space in between was simply not part of the theory. It was a model built on prohibition rather than explanation. The electron does not radiate because we say it does not radiate. It only occupies certain orbits because we say those are the only orbits allowed. Why? Because otherwise the math does not work. That kind of reasoning makes physicists deeply uncomfortable. It works, sure, but it does not explain. And physics is supposed to explain. By the early 1920s, a handful of younger physicists started pushing harder. They wanted to know what the electron was actually doing. Not what orbit it occupied, but what it was. Was it a particle, a wave, something else? And if it was jumping between orbits, what was happening during the jump? Bohr had no answer. He would tell you the question itself was wrong, that asking what happens between measurements was meaningless because quantum mechanics only describes what you can measure. That answer did not satisfy everyone. Some people wanted a picture, a mechanism, a story that made sense. The person who gave them that story, or at least the beginning of one, was not a physicist at all. He was a French aristocrat with a PhD in history. Louis de Broglie came from one of the oldest noble families in France. His older brother Maurice was an experimental physicist who worked on X-rays, and Louis tagged along to his lab meetings out of boredom more than ambition. He was supposed to have a career in diplomacy or literature. Instead, he got interested in light. Specifically, he got interested in the strange fact that light behaved like a wave in some experiments and like a particle in others. The photoelectric effect, the one Einstein explained in 1905, required light to be made of particles, photons, little packets of energy that hit electrons and kicked them out of metals. But interference patterns, the kind you get when you shine light through two slits and watch it create alternating bright and dark bands on a screen, required light to be a wave. Waves interfere, particles do not. You could not have it both ways, except apparently you could, because light was doing both. De Broglie sat with that contradiction for years, and in 1923 he had a thought. If light, which everyone had assumed was a wave, could behave like a particle, then maybe particles, which everyone assumed were particles, could behave like waves. Maybe electrons were not just tiny balls of charge, maybe they had a wavelength. Maybe when an electron moved, it was not traveling along a trajectory like a bullet, it was propagating like a ripple. De Broglie worked out the math. He proposed that any particle with momentum, any object moving through space, had an associated wavelength. The wavelength was inversely proportional to the momentum. Heavy objects moving fast had wavelengths so short you could never detect them. A baseball does not diffract when you throw it, because its wavelength is a billion times smaller than an atom. But an electron, tiny and light, moving at the kinds of speeds electrons move inside atoms, would have a wavelength on the order of the size of the atom itself. That was not a small effect. That was the dominant effect. The electron was not a particle sitting in an orbit. It was a wave wrapping around the nucleus. He wrote it up as his doctoral thesis and submitted it to the University of Paris in 1924. His thesis committee had no idea what to make of it. The math was fine. The proposal was bizarre. One of the examiners sent a copy to Einstein and asked for his opinion. Einstein read it and wrote back immediately. He said de Broglie had lifted a corner of the Great Veil. The thesis passed. 3 years later, American physicists Clinton Davison and Lester Germer fired electrons at a nickel crystal and watched them diffract. Electrons, solid particles with mass and charge, created interference patterns. They behaved like waves. De Broglie won the Nobel Prize in 1929. His idea, which had started as a wild speculative guess, turned out to be exactly right. Particles are waves, waves are particles. The distinction between the two is a human artifact, a leftover from classical physics that does not apply at quantum scales. De Broglie's hypothesis changed the picture of the atom completely. If the electron was a wave, then Bohr's orbits were not really orbits, they were standing waves. A standing wave is what you get when a wave reflects back on itself and interferes with its own reflections. Pluck a guitar string and the wave traveling down the string bounces off the ends and comes back. The incoming and outgoing waves overlap and create a pattern of nodes, places where the string does not move, and antinodes, places where it moves the most. Only certain wavelengths fit. If the wavelength does not divide evenly into the length of the string, the wave cancels itself out. The allowed wavelengths are the ones where the string V-tones in a stable pattern, 1 hump, 2 humps, 3 humps, and so on. Those are the harmonics. You can only play certain notes on a guitar string because only certain standing waves are stable. The electron in an atom works the same way. It is a wave wrapping around the nucleus. For the wave to be stable, it has to connect smoothly with itself after one full orbit. If it does not, the wave interferes destructively and cancels out. The electron is not there. The allowed orbits, the ones Bohr had simply declared by fiat, are the ones where an integer number of wavelengths fit evenly around the circumference of the orbit. 1 wavelength, 2 wavelengths, 3 wavelengths. Those are the stable configurations. Everything else is forbidden, not because of some arbitrary quantum rule, but because the electron is a wave, and waves do not exist in configurations where they destructively interfere with themselves. Bohr's quantization condition, the one that said the angular momentum of the electron had to be an integer multiple of Planck's constant divided by 2 pi, fell out naturally from de Broglie's wave picture. You did not have to assume it. It was a consequence of the electron being a wave. Suddenly, the quantum leap made sense, or at least it made more sense. When an electron jumps from one orbit to another, it is not a particle hopping from one track to another. It is a wave shifting from one standing wave pattern to another. The wave in the high-energy orbit stops existing. The wave in the low-energy orbit starts existing. The transition is not a movement through space, it is a change in the shape of the wave. That still does not give you a mechanism. It does not tell you why or when the jump happens, but it removes the weirdest part of Bohr's picture, the idea that a particle teleports from one place to another without crossing the gap. There is no particle, there is a wave, and waves can change shape without moving. De Broglie's idea was elegant. It unified particles and waves. It explained Bohr's quantization. It gave physicists a reason to take the quantum rules seriously. But it also raised a much harder question. If the electron is a wave, what is waving? Water waves are oscillations in the height of the water. Sound waves are oscillations in air pressure. Light waves, according to Maxwell, are oscillations in the electromagnetic field. But an electron is not light. It is not a disturbance in a field that already exists. It is a particle. Or it was supposed to be a particle. Now it is a wave. So what exactly is oscillating? De Broglie did not have an answer. He called it a pilot wave. a kind of guiding field that steered the particle, but he could not specify what the field was made of or how it worked. That gap would haunt quantum mechanics for decades, and it would eventually lead to one of the most counterintuitive ideas in the history of science. The thing that is waving is not a physical substance, it is probability. The wave does not describe where the electron is, it describes where the electron might be if you looked. But that realization was still a few years away. First, someone had to figure out what the rules of the wave were, how it evolved, how it interacted with the nucleus, how it produced the energy levels Bohr had found. That someone was not de Broglie. It was Werner Heisenberg, and he approached the problem from the exact opposite direction. Heisenberg was 23 years old in 1925, a graduate student working with Max Born at the University of Göttingen in Germany. He was brilliant, competitive, and temperamentally allergic to abstract philosophy. He did not care what the electron was. He cared about what you could measure. Bohr's model worked for hydrogen, but it was a mess for anything more complicated. Heisenberg wanted a theory that did not rely on visualizing orbits or trajectories or any of the classical baggage that kept breaking down. He wanted a set of mathematical rules that connected observations to other observations without requiring you to tell a story about what was happening in between. If you measure the energy of an electron in one state and then you measure it again in another state, the theory should tell you the probability of the transition and the wavelength of the emitted photon. That is all. No orbits, no paths, no pictures. Just the numbers you can actually measure in the lab. In June 1925, Heisenberg had a severe allergy attack and took a leave to Heligoland, a tiny treeless island in the North Sea. He spent 2 weeks alone, recovering, hiking, and thinking about the hydrogen spectrum. He realized that if you stopped trying to describe where the electron was and instead focused on the transitions between states, you could organize all the observable quantities, energies, wavelengths, intensities into a mathematical object, not a function, not a single number, a table of numbers, an array, a matrix. Each entry in the matrix represented a possible transition between two quantum states. Multiply the matrices according to certain rules, and you got the probabilities of more complicated transitions. It was abstract, it was ugly, it worked. Heisenberg rushed back to Göttingen, wrote it up, and handed the paper to Max Born. Born looked at it and recognized the mathematical structure immediately. Heisenberg had reinvented matrix algebra, a branch of mathematics that had been around for decades but had never been applied to physics. Born and his assistant Pascual Jordan cleaned up the formalism and extended it. By the end of the year, they had a complete theory of quantum mechanics. No orbits, no electron positions, just matrices representing observable quantities and rules for how those matrices evolved in time. The theory made predictions, lots of them, and every single one matched the experimental data. The hydrogen spectrum fell out exactly. The intensities of the spectral lines, which Bohr's model could not predict, fell out exactly. Even the fine structure, the tiny splitting of certain spectral lines caused by relativistic effects and electron spin, started to make sense. Heisenberg's matrix mechanics was the first fully quantum theory of the atom. It did not borrow from classical physics. It did not assume orbits or trajectories. It started from scratch and built a framework where the only things that existed were the things you could measure. Position was not a property the electron had when you were not looking. It was something that appeared when you performed a measurement. Momentum was the same. Energy, angular momentum, every observable quantity, they were all represented by matrices, and the matrices did not commute. That last part turned out to be critical. In ordinary arithmetic, the order of multiplication does not matter. 3 times 5 is the same as 5 times 3, but matrix multiplication is different. If you multiply matrix A by matrix B, you get one result. Multiply B by A, and you might get a completely different result. The order matters. Heisenberg found that the position matrix and the momentum matrix did not commute. Measure position first, then momentum, and you get a different result than if you measure momentum first, then position. That was not a feature of the math. It was not a quirk of the notation. It was a statement about reality. You cannot know both position and momentum exactly at the same time, because the act of measuring one disturbs the other. The more precisely you pin down where the electron is, the less precisely you can know how fast it is moving. The more precisely you measure its momentum, the more uncertain its position becomes. This was not measurement error. This was not a limitation of your instruments. It was a fundamental limit built into the structure of nature. Heisenberg called it the uncertainty principle, and it was not optional. Here is how it works. Position and momentum are represented by matrices that do not commute. The difference between measuring position then momentum and measuring momentum then position is proportional to Planck's constant. Planck's constant is tiny, so the effect is invisible at human scales. But at the scale of an electron, it is enormous. The uncertainty in position times the uncertainty in momentum is always greater than or equal to Planck's constant divided by 4 pi. You can write that in plain language without symbols, but the point is the product of the two uncertainties has a lower limit. You can make one uncertainty very small, but only by making the other one very large. You can never make both of them zero. There is no state where the electron has a definite position and a definite momentum. Such a state does not exist, not because we are bad at measuring, because the universe does not allow it. This has immediate consequences for the atom. In the classical picture, the electron spirals into the nucleus because it loses energy and slows down. Eventually, it reaches the nucleus. Position equals 0. Momentum equals 0, and the atom collapses. Heisenberg's uncertainty principle says that cannot happen. If you try to confine the electron to a very small region, say the size of the nucleus, you are making the uncertainty in its position very small. The uncertainty principle responds by making the uncertainty in its momentum very large. A large uncertainty in momentum means the electron could have a wide range of possible momenta, including very high momenta. High momentum means high kinetic energy. So the more you try to squeeze the electron into a smaller space, the more kinetic energy it has. At some point, the kinetic energy cost of confining the electron becomes larger than the potential energy gained by moving it closer to the nucleus. The electron reaches an equilibrium. It sits in the lowest energy state that is consistent with the uncertainty principle, and it stays there. That state is the ground state of the atom. It is stable, not because the electron is sitting still, but because quantum mechanics will not let it sit still. The electron has unavoidable quantum motion, a jittering, a fuzziness, that prevents it from ever collapsing into the nucleus. You can calculate the size of the ground state orbit using just the uncertainty principle. Assume the electron is confined to a region of size roughly equal to the Bohr radius, about 1/10 of a nanometer. The uncertainty in position is that size. The uncertainty in momentum is at least Planck's constant divided by the uncertainty in position. That gives the electron a minimum kinetic energy. The potential energy from the electromagnetic attraction to the nucleus pulls the electron inward, but the kinetic energy from the uncertainty principle pushes it outward. Minimize the total energy and you get the Bohr radius. The size of the atom is set by the balance between quantum uncertainty and electromagnetic attraction. If you try to make the atom smaller, the uncertainty principle makes the kinetic energy blow up. If you try to make it larger, the electromagnetic attraction pulls it back in. The ground state is the sweet spot where the two forces balance, and once the electron is in that state, it has nowhere lower to go. It cannot collapse, because collapsing would violate the uncertainty principle. This is why atoms are stable, not because of some arbitrary rule Bohr made up, because the laws of quantum mechanics forbid the electron from having a precisely defined zero momentum state at the nucleus. The electron is always moving, always spread out, always uncertain, and that uncertainty is what holds the atom together. It is one of the most beautiful results in physics. The thing that saves matter from collapsing is the same thing that makes the universe fundamentally unpredictable. You cannot know everything about a quantum system. The act of pinning down one property makes another property blur. And that blurriness, that quantum fuzz, is not a bug. It is the feature that makes chemistry possible. Heisenberg published the uncertainty principle in 1927 in a paper that is still taught in every undergraduate quantum mechanics course. The derivation is simple, the implications are staggering. The principle does not just apply to position and momentum. It applies to any pair of quantities that are represented by non-commuting matrices, energy and time, for instance. The more precisely you try to measure the energy of a quantum state, the less precisely you can define the moment in time when that measurement occurred. That has consequences for virtual particles, quantum fluctuations, the whole zoo of strange effects that show up when you take quantum mechanics seriously at short time scales. But the core insight is the one that matters for the atom. You cannot pin down both where the electron is and how fast it is moving. And because you cannot, the electron cannot spiral into the nucleus. It cannot have zero momentum at zero distance. The universe will not let it. Einstein hated the uncertainty principle, not because it was wrong. The math was airtight. He hated it because it implied that nature was fundamentally indeterminate. You could not, even in principle, predict the exact outcome of a quantum measurement. You could only predict probabilities. The electron might be here, or it might be there, and until you looked, it was in some sense in both places at once, or in neither place, or in a cloud of places weighted by probability. The classical picture, where particles had definite positions and momenta and trajectories, was gone, replaced by a picture where particles were smeared out, indefinite, only snapping into definite states when you forced them to by performing a measurement. Einstein famously said that God does not play dice with the universe. Bohr shot back that Einstein should stop telling God what to do. The argument between the two of them would last for decades, and it is still not entirely settled. But the experiments are unambiguous. The uncertainty principle is real. You can test it. People have tested it. It works every single time. The principle also explains why the electron does not radiate when it sits in a stable orbit. In the classical picture, an accelerating charge radiates because it has a definite trajectory, and that trajectory involves continuous acceleration toward the center. But in the quantum picture, the electron does not have a trajectory. It does not have a definite position or a definite momentum. It is not accelerating in the classical sense. It is sitting in a quantum state, a standing wave, a cloud of probability that does not change with time as long as you leave it alone. No change, no radiation. The electron only radiates when it transitions to a lower energy state, and even then, the radiation is not continuous. It is a single photon emitted in a quantum jump. The energy of the photon is exactly equal to the difference in energy between the two states, no more, no less. The process is quantized, discrete, not smooth, and the uncertainty principle is part of the reason why. The electron cannot smoothly transition between states because it does not have a smooth path. It has a set of discrete allowed states, and it switches between them. The switch is governed by probabilities, not certainties, but the switch is real. By the late 1920s, the picture of the atom had changed completely. Bohr's orbits were gone. The electron was not a particle moving on a track. It was a wave, or a cloud, or a probability distribution, depending on how you wanted to think about it. The definite trajectory was gone. The definite position was gone. What replaced them was a quantum state described by a mathematical object that encoded all the information you could possibly know about the system. That object was not a matrix, at least not the way Heisenberg had used matrices. It was a wave function, and the equation governing how it evolved was written down by Erwin Schrödinger in 1926. Schrödinger's equation and Heisenberg's matrices turned out to be two different mathematical representations of the same underlying physics. You could use either one. They gave the same answers. But Schrödinger's version was easier to visualize, and it became the standard way of teaching quantum mechanics. The uncertainty principle sits at the heart of that description. It is not an add-on. It is not a correction. It is built into the structure of the theory. The wave function describes a spread of possible outcomes, and the width of that spread is controlled by the uncertainty principle. You can make the wave function narrow in position, but then it has to be wide in momentum. You can make it narrow in momentum, but then it has to be wide in position. The wave function cannot be a spike, a delta function, localized at a single point with a single momentum. That state is forbidden. The universe does not allow it. And because it does not allow it, matter is stable. Atoms do not collapse. Electrons do not spiral into the nucleus. The quantum fuzz, the unavoidable uncertainty, is what holds everything together. Your body exists because Heisenberg discovered that you cannot know everything. The fact that the universe is fuzzy at its core is the reason chemistry works. The reason molecules bond. The reason stars burn hydrogen into helium instead of just collapsing into black holes. The reason there is structure, complexity, life. Heisenberg was 25 years old when he figured this out. 25. He won the Nobel Prize in 1932. By that point, quantum mechanics was the dominant framework in atomic physics, and the uncertainty principle was one of its cornerstones. But the principle still bothered people. It bothered Einstein for the rest of his life. It bothered a whole generation of physicists who had grown up with classical determinism and could not quite let go of the idea that particles should have definite properties, whether you measured them or not. The debates raged for decades. Eventually, experiments settled the matter. The uncertainty principle is not a philosophical position. It is a fact about nature. And once you accept it, the rest of quantum mechanics falls into place. The electron is not a particle in an orbit. It is a wave in a probability cloud. The cloud has a shape, and that shape is determined by an equation that describes not where the electron is, but where it might be. And the place to look for that equation is not in Heisenberg's matrices, it is in Schrödinger's wave. Heisenberg had shown that you could not know both where the electron was and how fast it was moving. The uncertainty principle worked. It explained why atoms did not collapse. It explained why the electron could not spiral into the nucleus. It solved the stability problem by declaring that certain kinds of knowledge were fundamentally off-limits. You could measure position, or you could measure momentum, but not both, and the product of the uncertainties in those measurements would always be larger than a fixed minimum set by Planck's constant. That was the rule. It was built into the structure of reality. And it meant that the classical picture of particles with definite positions and definite speeds was wrong at quantum scales. The electron did not have a trajectory. It did not sit at a specific point, moving at a specific velocity. It was smeared out, fuzzy, indefinite. Heisenberg's matrix mechanics captured that fuzziness mathematically, but it was abstract. Matrices, operators, non-commuting observables. The formalism worked, but it was hard to visualize. And physicists, for all their mathematical sophistication, are still human. They want pictures, they want a story. They want to know what the electron is doing, not just what you can measure about it. Erwin Schrödinger gave them that picture. Or at least he gave them something closer to a picture than Heisenberg's matrices ever could. Schrödinger was not trying to compete with Heisenberg. He was trying to solve the same problem from a completely different angle. He was a physicist at the University of Zurich in Switzerland, 40 years old in 1925, older than most of the other players in the quantum revolution. He was a classical physicist by training, steeped in thermodynamics and electromagnetic theory. He had spent years thinking about waves, oscillations, the kinds of differential equations that describe how systems evolve smoothly in time and space. When he heard about de Broglie's matter wave hypothesis, the idea that particles like electrons had an associated wavelength, Schrödinger saw an opening. If the electron was a wave, then it should obey a wave equation, not a matrix equation. Not an algebraic rule about what you can and cannot measure. A proper differential equation that described how the wave evolved, where it was allowed to be, what shape it took. Schrödinger sat down in late 1925 and started looking for that equation. By January 1926, he had it. The story goes that he spent the Christmas holiday of 1925 at a villa in the Swiss Alps with a mysterious companion, possibly a former girlfriend, though the details are murky because Schrödinger kept that part of his life private. What is not murky is that he came back with the wave equation fully formed, written out in a series of papers that he submitted to Annalender Physik over the next few months. The first paper appeared in January 1926. By June, he had published 4 more, each one extending the formalism and showing how it applied to different physical systems. The papers were dense, rigorous, and elegant. They did not read like someone groping in the dark. They read like someone who had seen the answer and was simply writing it down. Schrödinger had found the equation that governed quantum waves, and the equation did everything Heisenberg's matrices did, but it did it in a language physicists already understood. Wave equations, differential operators, boundary conditions, this was familiar territory. You could work with it, you could visualize it, and most importantly, you could apply it to real atoms and get real predictions. The equation itself looks deceptively simple if you are used to reading mathematical physics. But since we are speaking this out loud, here is what it says in words. The equation describes how the wave function of a quantum system changes with time. The wave function is the central object in Schrödinger's theory. It is a mathematical function that assigns a complex number to every point in space at every moment in time. That complex number encodes everything you can know about the system. The wave function is not the electron. It is not a physical wave in the way sound waves are physical. It is a probability wave, though Schrödinger himself did not realize that at first. He thought the wave function represented a real spread-out electron, a cloud of charge smeared over space. That interpretation turned out to be wrong. The correct interpretation came from Max Born a few months later. Born pointed out that the wave function itself was not directly observable. What you could measure was the square of its magnitude, and that square gave you the probability of finding the electron at a particular location if you looked. The wave function was a map of possibilities, not a map of stuff. That realization changed everything. It meant that before you measured the electron's position, the electron did not have a position. It had a probability distribution. It was not located at a single point. It was in a superposition of many possible locations, weighted by the wave function. When you performed a measurement, the wave function collapsed. It went from a spread-out cloud of possibilities to a single sharp spike at the location where you detected the electron. The collapse was instantaneous, non-local, and deeply strange, but it matched the experiments. And once you accepted it, Schrödinger's equation became the most powerful tool in quantum mechanics. The equation comes in two forms. One is time-dependent, describing how the wave function evolves as time passes. The other is time-independent, describing the allowed shapes the wave function can take when the system is in a stable state. The time-independent version is the one that matters for atoms because atoms in stable states do not change with time. The electron in the ground state of hydrogen sits in a particular wave function configuration, and it stays there until something perturbs it. That wave function is a solution to the time-independent Schrödinger equation. Finding the solutions means solving a differential equation with boundary conditions. The boundary conditions come from the physical setup. The electron is bound to the nucleus by the electromagnetic force, so the wave function has to go to zero, far from the nucleus. The electron cannot be infinitely far away. It has to be localized near the atom. Those constraints, combined with the equation itself, limit the possible solutions. Not every function is allowed. Only specific functions satisfy the equation and the boundary conditions. Those specific functions are the quantum states of the atom, the allowed energy levels, the orbitals. Schrödinger applied his equation to the hydrogen atom and solved it exactly. The hydrogen atom is simple enough that you can write down the solutions in closed form. They involve special functions, polynomials multiplied by exponentials, things with names like Laguerre polynomials and spherical harmonics. But the math is tractable and the results are exact. What Schrödinger found was that the allowed energy levels matched the ones Bohr had predicted exactly. The ground state energy, the first excited state, the second excited state, all the way up, every single one agreed with Bohr's formula. That was the first major success. Schrödinger had derived Bohr's quantization condition without assuming it. It fell out of the wave equation naturally as a consequence of the boundary conditions. The electron could only occupy certain energy levels because those were the only levels where the wave function was a stable standing wave that did not blow up or cancel itself out. But Schrödinger's equation gave more than just the energy levels, it gave the shapes of the orbitals. The wave function for each state was a specific mathematical function of position, and you could plot it. You could visualize what the electron's probability distribution looked like, and this is where the picture of the atom changed from something abstract to something you could almost see. The ground state of hydrogen, the lowest energy state, is called the 1s orbital. The 1 refers to the principal quantum number, a label that tells you which energy level you are talking about. The s refers to the angular momentum quantum number, which in this case is 0. Zero angular momentum means the orbital is spherically symmetric. It looks the same in every direction. The wave function for the 1s orbital is a simple exponential that decays as you move away from the nucleus. Close to the nucleus, the probability is highest. Far from the nucleus, it drops off smoothly, never quite reaching 0 but getting smaller and smaller the farther out you go. If you plotted the probability density, the square of the wave function, it would look like a fuzzy sphere centered on the nucleus. The electron is not at a single point. It is spread out in a cloud. Most of the time, if you measured it, you would find it close to the nucleus. but occasionally you might find it farther out. The cloud does not have a sharp edge. It fades gradually into the surrounding space. That is the quantum orbital. Not an orbit in the classical sense, where the electron moves in a circle like a planet around the sun. An orbital is a region of space where the electron is likely to be found. It is a probability cloud, a map of where the electron might show up if you looked. The distinction between orbit and orbital is not just semantic, it is fundamental. The electron does not move around the nucleus on a track. It does not have a path. It exists as a standing wave, a static configuration that fills a region of space. The wave does not travel. It just sits there, vibrating in place, if vibrating is even the right word. The wave function oscillates in time at a frequency proportional to the energy of the state, but the probability distribution, the thing you can actually measure, does not change. The electron is in a stationary state. It is spread out, but it is not moving in the classical sense. The once orbital is the simplest. Higher energy states have more complicated shapes. The 2's orbital, the next one up, is also spherically symmetric, but it has a node. A node is a place where the wave function goes to zero. In the 2's orbital, there is a spherical shell at a certain radius where the probability drops to zero. Inside that shell, the wave function has one sign. Outside, it has the opposite sign. The probability density, the square of the wave function, has two peaks, one close to the nucleus, one farther out. The electron in a 2s state is most likely to be found in one of those two regions. The node in between is a forbidden zone, not because something is blocking the electron, but because the wave function itself is zero there. The electron is never there. Or more accurately, if you measured it, you would never find it there. The probability is exactly zero. Then there are the p orbitals. These have angular momentum. They are not spherically symmetric. The wave functions for p orbitals depend on direction as well as distance from the nucleus. There are 3 of them, usually labeled p sub x, p sub y, and p sub z, corresponding to the 3 spatial directions. Each one has a dumbbell shape. 2 lobes on opposite sides of the nucleus, separated by a node at the center. The electron in a p orbital is most likely to be found in one of the 2 lobes. It is never found at the nucleus itself. The wave function goes to zero there. That makes sense if you think about angular momentum. Angular momentum is motion around a center. If the electron has angular momentum, it is not sitting at the center, it is circling around it. Or more accurately, its probability distribution is shaped like something circling around it. The lobes of the p orbital extend along one of the 3 axes, and the electron could be in either lobe. The probability is spread evenly between them, until you measure it. Then the wave function collapses, and you find the electron in one lobe or the other. But before the measurement, it was in both, or in neither, or in the entire dumbbell-shaped cloud. The language we use to describe this breaks down because we do not have good words for what a superposition is. The electron is not in one place. It is not in 2 places. It is in a state described by a wave function that assigns probabilities to many places, and that is all you can say. Higher energy states have even more complicated shapes. The d orbitals have angular momentum quantum number 2. There are 5 of them. They have shapes with 4 lobes, or rings, or cloverleaf patterns. The f orbitals are worse. 7 of them, even more baroque. The shapes get increasingly intricate as you go up in energy and angular momentum, but the underlying principle is the same. The wave function is a solution to Schrödinger's equation. The square of the wave function gives the probability density. The regions where the probability is high are where you are likely to find the electron. The nodes, the places where the wave function is zero, are where you will never find it. The orbital is the shape of that probability cloud. And the chemistry of the atom, the way it bonds with other atoms, the way it behaves in molecules, all of that depends on the shapes of the orbitals in the outermost energy levels. Each orbital is labeled by a set of quantum numbers. The principal quantum number, n, tells you the energy level. n equals 1 is the ground state. n equals 2 is the first excited state. n equals 3 is the second excited state, and so on. The angular momentum quantum number, usually written as L, tells you the shape. L equals 0 is an s orbital, spherically symmetric. L equals 1 is a p orbital, dumbbell-shaped. L equals 2 is a d orbital, more complex. L equals 3 is an f orbital, even more complex. The magnetic quantum number, m sub L, tells you the orientation. For a p orbital, there are 3 possible orientations along the x, y, or z axis. For a d orbital, there are 5. For an f orbital, 7. And finally, there is the spin quantum number, m sub s, which can be either +1/2 or -1/2. Spin is a quantum property that has no classical analog. The electron behaves as if it is spinning, but it is not actually spinning in the way a ball spins. Spin is intrinsic angular momentum, a quantum number that the electron carries, and it can point either up or down relative to some chosen axis. Each orbital can hold 2 electrons, one with spin up and one with spin down. That is the Pauli exclusion principle, another quantum rule that has no classical explanation. No 2 electrons in an atom can have the same set of quantum numbers. Once an orbital is filled with 2 electrons, one spin up and one spin down, you have to move to the next orbital. The combination of these quantum numbers, n, l, m sub l, and m sub s, specifies the state of an electron completely, and the collection of all the occupied orbitals in an atom determines its electron configuration. Hydrogen has 1 electron in the 1s orbital. Helium has 2 electrons in the 1s orbital, 1 spin up, 1 spin down. Lithium has 2 electrons in the 1s orbital and 1 in the 2s orbital. As you move up the periodic table, adding more protons to the nucleus and more electrons to balance the charge, the orbitals fill up in a specific order. The order is not always what you would expect, because the energies of orbitals with the same n but different L can be very close, and interactions between electrons can shift the order, but the pattern is predictable. As orbitals fill first, then p orbitals, then d orbitals, then f orbitals. The structure of the periodic table, the rows and columns, the groups of elements with similar chemical properties, all of it comes from the filling order of the orbitals. Elements in the same column have the same configuration of outermost electrons. That is why they behave the same way chemically. Sodium and potassium are both in the first column of the periodic table because they both have 1 electron in an s orbital outside a filled shell. That 1 electron is easy to remove, which is why both elements are highly reactive metals. Neon and argon are in the last column because their outermost orbitals are completely filled. No electrons are easy to add or remove, which is why they are inert gases. Schrödinger's equation explained all of this, not by telling a story about electrons hopping from orbit to orbit, but by describing the wave functions and showing how they filled up according to quantum rules. The atom was not a miniature solar system. It was a nucleus surrounded by a set of probability clouds, each cloud corresponding to an allowed quantum state, and each state occupied by at most 2 electrons. The clouds overlapped. They interpenetrated. They did not collide because they were not physical objects. They were mathematical functions describing where electrons might be found. The picture was strange, abstract, hard to hold in your head, but it worked. It explained the periodic table. It explained why atoms bonded the way they did. It explained why some elements were metals and others were insulators. It explained why oxygen liked to grab 2 electrons and form water. It explained why carbon could form 4 bonds and build the complex molecules that make life possible. All of it came from the shapes of the orbitals and the rules for how they filled up. Schrödinger published his wave mechanics in early 1926. By the summer, physicists were using it to solve problems Bohr's model could not touch. Multi-electron atoms, molecules, chemical bonds, the harmonic oscillator, the hydrogen molecular ion. Every system they tried, the equation worked. It gave accurate predictions for energy levels, transition probabilities, spectral lines. And unlike Heisenberg's matrix mechanics, which was algebraically rigorous but hard to visualize, Schrödinger's equation gave you something you could plot. You could draw the orbitals. You could color-code the regions of high and low probability. You could make pictures. Physicists loved pictures. Within a year, Schrödinger's formulation had become the standard way of teaching quantum mechanics, and it still is. Every undergraduate physics major learns the Schrödinger equation. They solve it for the hydrogen atom. They plot the orbitals. They learn the quantum numbers. The formalism is embedded so deeply in the way we think about atoms that it is hard to remember there was ever a time when it did not exist. But there was a problem. The same problem that had plagued every attempt to understand quantum mechanics since Planck first introduced the quantum in 1900. The wave function was a mathematical object, a function that assigned complex numbers to points in space. But what was it? What did it represent physically? Schrödinger thought it was a real physical wave, a spread-out distribution of charge. He imagined the electron as a cloud, literally smeared over space, with the wave function describing the density of the cloud. But that interpretation did not work. If the electron was really spread out like a cloud, then when you measured its position, you should find little bits of electron all over the place. You do not. You always find the entire electron at a single point. The electron has a definite charge, a definite mass. You never detect half an electron or a tenth of an electron. You detect the whole thing, localized at one spot. So the wave function cannot be a description of how the electron is physically distributed. It has to be something else. Max Born figured out what it was. Born was a theoretical physicist at the University of Göttingen, Heisenberg's mentor, and one of the key developers of matrix mechanics. In June 1926, he published a paper proposing a new interpretation of the wave function. He said the wave function was not a physical wave, it was a probability wave. The square of the wave function at a given point in space gave the probability density for finding the electron at that point, if you measured its position. High probability where the wave function was large. Low probability where it was small. Zero probability where the wave function was zero. That was it. The wave function did not describe what the electron was doing. It described what you would find if you looked. Before the measurement, the electron did not have a definite position. It was in a superposition of all possible positions, weighted by the wave function. The measurement forced it to pick one. The wave function collapsed from a spread-out cloud to a sharp spike at the location where the electron was detected, and the probability of detecting it at any particular location was given by the square of the wave function at that location. This interpretation solved the measurement problem, but it introduced a much deeper mystery. If the wave function described probabilities rather than physical reality, then what was the electron before you measured it? Was it nowhere? Was it everywhere? Was it in a kind of limbo, neither here nor there, waiting for a measurement to bring it into existence? The standard answer, the one that became known as the Copenhagen interpretation because Bohr and Heisenberg developed it in Copenhagen, was that asking what the electron was doing before the measurement was a meaningless question. Quantum mechanics only described the results of measurements. It did not describe an underlying reality that existed independently of observation. The electron did not have a position until you measured it. Position was not a property the electron possessed. It was a property that emerged from the interaction between the electron and the measuring apparatus. Before the interaction, there was only the wave function. After the interaction, there was a definite outcome. The wave function collapsed, and you could not predict which outcome you would get. You could only predict the probabilities. Einstein hated this. He hated the idea that reality was fundamentally probabilistic. He hated the idea that particles did not have definite properties until you looked at them. He spent the rest of his life trying to prove that quantum mechanics was incomplete, that there was a deeper layer underneath, a set of hidden variables that determined the outcomes of measurements in a way that only looked random because we could not see the variables. He never succeeded. Every experiment designed to test the predictions of quantum mechanics came out in favor of the Copenhagen interpretation. The electron really does not have a definite position until you measure it. The wave function really does collapse. Probability is not ignorance, it is built into the fabric of reality. Schrödinger was not thrilled with the probability interpretation either. He had hoped his wave equation would provide a return to classical determinism, a way of describing the electron as a real physical wave that evolved smoothly and predictably. Instead, Born's interpretation turned the wave function into a ghost, a mathematical tool for calculating probabilities with no clear physical referent. Schrödinger tried for years to come up with a better interpretation. He never found one. In 1935, frustrated by the direction the field was going, he wrote a paper describing a thought experiment involving a cat in a box with a vial of poison triggered by a quantum event. The cat, according to the Copenhagen interpretation, would be in a superposition of alive and dead until someone opened the box and looked. Schrödinger thought this was absurd. He was trying to show that the probability interpretation led to ridiculous conclusions when applied to macroscopic objects. Instead, his thought experiment became one of the most famous illustrations of quantum weirdness. Schrödinger's cat is now a cultural icon, a symbol of the strangeness at the heart of quantum mechanics. But the equation itself, the wave equation Schrödinger derived in 1926, that was real. It worked. It still works. It is the foundation of all of modern chemistry, materials science, and a huge chunk of physics. The orbitals it predicts, the probability clouds, the quantum numbers, all of that is confirmed by experiment to absurd precision. You can take an image of an orbital now using scanning tunneling microscopes. You can see the lobes, the nodes, the shapes Schrödinger's equation predicted a century ago. They are real, not in the sense that the electron is sitting in a cloud. In the sense that if you measure where the electron is over and over again, building up a statistical distribution of measurements, the pattern you get matches the square of the wave function exactly. The electron is spread out as a probability, and Schrödinger's equation describes that spread. So where does that leave us? The atom is not a solar system. The electron is not a particle on an orbit. It is a quantum object described by a wave function that evolves according to Schrödinger's equation. The wave function assigns probabilities to different positions, and when you measure the position, you get one outcome drawn from that probability distribution. The orbitals, the allowed states, are solutions to the equation with specific shapes and specific energies. Those shapes determine chemistry. They determine how atoms bond, how molecules form, how proteins fold, how DNA replicates. Every chemical reaction you have ever heard of, every biological process in your body, depends on the shapes of electron orbitals and the rules for how they overlap and interact. Schrödinger gave us the tool to calculate those shapes. Bohr gave us the interpretation that made sense of what the tool was telling us. And between the two of them, they completed the picture of the atom that Bohr had started. The electron was no longer a ghost, it was a wave function, a cloud of probability anchored to the nucleus by the electromagnetic force and shaped by the boundary conditions of Schrödinger's equation. It did not collapse into the nucleus because the uncertainty principle would not let it. It did not radiate because it was sitting in a stationary state, a standing wave that did not change with time. It occupied discrete energy levels because those were the only levels where the wave function satisfied the boundary conditions. And it filled up the periodic table in a predictable order because each orbital could hold 2 electrons and no more. And once an orbital was full, you moved to the next one. The atom was stable, the atom was explainable, the atom made sense. Not in the way classical physics made sense, with definite positions and definite trajectories and a clockwork universe ticking along predictably, in a new way, a quantum way, where particles were waves, waves were probabilities, and the act of measurement was woven into the fabric of reality itself. Schrödinger's wave was the electron's quantum home, not a place, but a space of possibilities. And that space, governed by an equation written down in 1926 by a physicist on a winter holiday in the Alps, turned out to be the structure underneath everything, the reason chemistry works, the reason atoms bond, the reason you exist. The equation did not just describe the electron, it described the foundation of matter itself. And now the question was not whether the electron was a wave or a particle. The question was what the electron actually was. Because if it was not sitting at a point, and it was not spread out like a cloud, and it was not moving on a trajectory, then what exactly was this thing we had been calling a particle for the last 2,000 years? Schrödinger's equation told you where the electron might be if you looked. The wave function gave you probabilities, shapes, orbitals, a cloud of possible locations weighted by quantum rules, but it did not tell you what the electron actually was. And by the mid-20th century, after decades of quantum mechanics solving problem after problem with extraordinary precision, that question was still sitting there unanswered. Not what does the electron do, what is it? The classical picture was simple. The electron was a particle, a tiny ball of negative charge with a definite mass, a definite size, and a definite location at any given moment. You could not measure the location perfectly because of the uncertainty principle, but that was a limitation on your ability to measure, not a statement about whether the location existed. The particle was there. It had properties. It was a thing in the way a grain of sand is a thing, just smaller. That picture survived into the early days of quantum mechanics because people needed something to hold on to. Even after the wave function replaced the orbit, even after the probability interpretation replaced the idea of a definite trajectory, physicists still talked about the electron as if it were a particle, a point particle they called it, meaning it had no internal structure, no size, no parts. It was a mathematical point with charge and mass attached. That terminology stuck. And for a long time, nobody questioned it too carefully because the math worked and the experiments agreed with the predictions. But as measurement techniques got better, as particle accelerators got more powerful, as physicists started probing smaller and smaller scales, the question came back. Is the electron really a point? Does it have a size? And if it does not, what does that even mean? How can something with mass and charge take up zero volume? How can something with zero size interact with other particles, emit photons, participate in chemical bonds? The more you think about it, the less sense it makes. And yet that is what the data says. The electron, as far as anyone has been able to measure, is a point. No radius, no internal structure, no moving parts, just a location, a charge, and a mass. And that is it. Let's start with what we know for sure. The electron is classified as a lepton in the Standard Model of particle physics. The Standard Model is the current best description of all known particles and the forces that act on them, excluding gravity. It was assembled over the course of the 20th century from thousands of experiments and decades of theoretical work, and it has been tested to absurd precision. Every prediction the Standard Model makes about particle interactions has been confirmed. The Higgs boson, predicted in the 1960s, was finally detected in 2012 at the Large Hadron Collider, exactly where the model said it should be. The Standard Model works. It is not complete. It does not include gravity. It does not explain dark matter or dark energy. It does not explain why the universe has more matter than antimatter. But for the particles and forces it does describe, it is stunningly accurate. In the Standard Model, particles come in two broad categories: fermions and bosons. Fermions are the matter particles, bosons are the force carriers. The fermions are further divided into quarks and leptons. Quarks are the building blocks of protons and neutrons. They come in 6 types, or flavors, called up, down, charm, strange, top, and bottom. Quarks are never found in isolation. They are always bound together in groups of 2 or 3 by the strong nuclear force, forming composite particles called hadrons. Protons are made of 2 up quarks and 1 down quark. Neutrons are made of 1 up quark and 2 down quarks. The quarks inside a proton or neutron are constantly exchanging gluons, the force carriers of the strong interaction, and the whole system is a seething mess of quantum fields and virtual particles. The proton has structure, it has size. If you fire high-energy electrons at a proton, they scatter in ways that reveal the distribution of charge inside. The proton is not a point. It is a composite object with a radius of about 0.8 femtometers, roughly 0.8 times 10 to the negative 15 meters. That is incredibly small, but it is measurable. The electron is different. The electron is a lepton. Leptons are not made of quarks. They do not participate in the strong nuclear force. There are 6 leptons in the Standard Model, organized into 3 generations. The first generation contains the electron and the electron neutrino. The second generation contains the muon and the muon neutrino. The third generation contains the tau and the tau neutrino. Each generation is heavier than the one before, but otherwise the particles behave similarly. The muon is essentially a heavy electron. It has the same charge, the same spin, the same interactions. It just has about 200 times more mass, and it decays into an electron and neutrinos within a few microseconds. The tau is even heavier and even shorter lived. But all 3 charged leptons, the electron, the muon, and the tau, are treated in the Standard Model as fundamental particles. They are not made of smaller parts. They do not have internal structure. They are point particles. That designation, fundamental particle, is not a philosophical claim. It is an experimental observation. If a particle has internal structure, you can probe it by scattering other particles off it at high energies. The scattering pattern tells you how the charge and mass are distributed inside. That is how Rutherford discovered the nucleus. Alpha particles scattered off gold atoms at angles that revealed a tiny dense core. That is how physicists in the 1960s discovered quarks inside protons. Electrons fired at protons, scattered in ways that showed the proton was not a uniform blob. It had point-like constituents inside. The higher the energy of the collision, the smaller the scales you can probe. If you want to see whether a particle has structure at a distance scale of 1 femtometer, you need collision energies in the range of a few 100 million electron volts. If you want to probe 10 times smaller scales, you need collision energies 10 times higher. Modern particle accelerators can reach energies in the trillions of electron volts. That lets physicists probe distances down to about 10 to the negative 19 meters, a thousandth of a femtometer. At those scales, the proton is not point-like. It is a cloud of quarks and gluons, all interacting, all exchanging energy, a constantly shifting mess. The electron, by contrast, behaves exactly like a point at every energy scale we have tested. No internal structure has been detected. No scattering anomalies, no hint of smaller constituents inside. Collide electrons with positrons at high energies and they annihilate, producing photons or other particles. The process looks exactly like what you would expect from two-point charges meeting and converting their mass into energy. No deviations, no surprises. The current experimental upper limit on the electron's radius is about 10 to the negative 22 meters. That is a millionth of a billionth of a billionth of a meter. If the electron has a size, it is smaller than that, much smaller. The Standard Model treats it as having exactly zero size, and so far, no experiment has contradicted that assumption. But there is a catch. Saying the electron is a point particle does not mean it is a tiny dot sitting in space like a mathematical point. That image breaks down immediately when you remember that the electron is also a quantum object described by a wave function. The wave function is spread out. It occupies a region of space. The probability cloud for an electron in the ground state of hydrogen extends over a radius of about 0.5 angstroms, roughly 10 to the negative 10 meters. That is enormous compared to the scale at which the electron itself is believed to have zero size. So what does it mean to say the electron is a point if its wave function is spread out over a region millions of times larger? The answer is that the electron has no spatial extent of its own, but its quantum state can be delocalized. The wave function describes where the electron might be found if you measure its position. When you do measure it, you always find the entire electron at a single location. You never detect half an electron here and half an electron there. The electron is indivisible. It does not spread its charge over space like a cloud. The charge is always localized at a point when you look. But before you look, the electron exists in a superposition of many possible positions, and the probability of finding it at any given point is determined by the wave function. The wave function is extended. The electron, when measured, is a point. That duality is built into the structure of quantum mechanics. The electron is not a classical particle. It is not a little ball sitting somewhere. It is a quantum excitation in a field, and the field itself extends through all of space. The electron is a localized excitation in that field, but the excitation does not have internal parts. It is as simple as a disturbance in a field can be. That leads to another strange feature. The electron's charge, its mass, and its spin are properties of the excitation. They are not properties of something inside the electron. There is no inside. The electron does not have a little core where the charge lives and an outer shell where the mass lives. It is not structured that way. The charge is a property of the electron as a whole. The mass is a property of the electron as a whole. Spin, a quantum number that measures intrinsic angular momentum, is a property of the electron as a whole. None of these properties arise from the motion or arrangement of smaller parts, because there are no smaller parts. The electron is the smallest unit. It is elementary in the most literal sense. It cannot be divided. This is fundamentally different from composite particles like protons and neutrons. A proton is made of 3 quarks bound together by gluons. The quarks themselves are elementary particles as far as we know, but the proton is not. The mass of a proton is not the sum of the masses of its constituent quarks. Most of the proton's mass comes from the energy of the gluon field binding the quarks together. The strong force is so powerful that the energy stored in the field contributes more to the proton's mass than the quarks themselves do. The proton's charge, +1 in units of the elementary charge, comes from the charges of the quarks. 2 up quarks, each with charge +2/3, and 1 down quark with charge -1/3. Add them up and you get +1. The proton's spin, 1/2, comes from the combination of the spins and orbital angular momenta of the quarks and gluons inside. The proton's magnetic moment, a measure of how it responds to magnetic fields, depends on the internal motion of its constituents. All of this structure is measurable. You can probe it, you can see it in scattering experiments. The proton has moving parts, the electron has none of that. Its charge is -1 elementary charge, and it does not come from adding up the charges of smaller particles. It is the charge of the electron. Its mass is about 0.51 million electron volts, divided by the speed of light squared, and it does not come from the energy of internal interactions. It is the mass of the electron. Its spin is 1/2, and it does not come from the orbital motion of constituent particles. It is the intrinsic spin of the electron. These properties are inputs to the Standard Model, not outputs. You measure them experimentally and plug them into the equations. The theory does not predict their values, it just uses them. And the electron does not have substructure to explain where those values come from. It is a point. It has properties, that is all. Except physicists are not entirely comfortable with that answer. For one thing, it is incomplete. Saying the electron is a point particle is a statement about what we have measured so far, not a statement about ultimate reality. Every time measurement techniques improve, physicists probe smaller scales, and every time the electron still looks like a point. But there is always a limit to how small you can probe, set by the energy of your collisions and the sensitivity of your detectors. The current limit is about 10 to the -22 meters. Below that scale, we do not know. The electron could have structure we just have not seen yet. Or it could be truly structureless all the way down. There is no way to know without better experiments. More troubling is that the electron, despite being a point, has a finite mass and a finite charge. In classical electromagnetism, a point charge creates an electric field that diverges at the location of the charge. The energy stored in that electric field, calculated by integrating the field energy over all of space, turns out to be infinite. That is a problem. If the electron is a point, and its electric field energy is infinite, then the electron's mass, which is related to its energy through Einstein's equation energy equals mass times the speed of light squared, should also be infinite. It is not. The electron has a perfectly finite mass of about 9 × 10 to the -31 kilograms. So either the electron is not really a point, or classical electromagnetism breaks down at very short distances, or something more subtle is happening that we do not fully understand. The resolution, as it turns out, comes from quantum field theory. In quantum field theory, particles are not little balls, they are excitations in fields, and the fields themselves are quantized. The infinities that show up in classical calculations get absorbed into a process called renormalization, where you redefine the parameters of the theory in a way that makes the observable quantities finite. Renormalization works, but it is not entirely satisfying. It feels like sweeping the problem under the rug. The infinities are still there in the raw equations. You just rearrange them in a way that makes the final answers come out finite and correct. Quantum electrodynamics, the quantum field theory of electrons and photons, is renormalizable. That is part of why it works so well. But the fact that you need to do this at all is a hint that something deeper is going on. There is also the matter of the electron's magnetic moment. Every charged particle with spin has a magnetic moment, a measure of how strongly it interacts with magnetic fields. You can think of the electron as a tiny spinning charge, though again, it is not literally spinning in the classical sense. The spin is intrinsic, a quantum property. But the spin creates a magnetic moment, and you can calculate what that moment should be using Dirac's equation, the relativistic version of Schrödinger's equation that describes the electron. Dirac's equation predicts a magnetic moment proportional to the electron's spin and inversely proportional to its mass. That prediction is called the Dirac magnetic moment, and it is very close to the experimentally measured value, but not exactly. The measured magnetic moment is slightly larger, by about 1 part in 1,000. That tiny discrepancy is not an error. It is real, and it comes from quantum corrections. The electron, even though it is a point particle, interacts with the quantum vacuum. The vacuum, according to quantum field theory, is not empty. It is filled with virtual particles popping in and out of existence on timescales too short to directly observe. Virtual electron-positron pairs, virtual photons, a seething froth of quantum fluctuations. The electron interacts with those fluctuations, and they modify its magnetic moment slightly. Calculating the correction requires summing over all possible virtual processes, a series of increasingly complicated diagrams called Feynman diagrams. The first correction, from a single virtual photon, increases the magnetic moment by about 0.12%. Higher order corrections add smaller and smaller contributions. Calculating the magnetic moment to 11 significant figures, the current state of the art, requires summing thousands of Feynman diagrams and took decades of work. The theoretical prediction and the experimental measurement agree to better than 1 part in 1 trillion. It is the most accurately tested prediction in all of science, and the entire calculation treats the electron as a structureless point. If the electron had internal structure, the calculation would not work. The agreement is indirect evidence that the electron really is elementary. But that precision also raises a deeper question. If the electron is truly a point with zero size, then what is it? Not what is it made of, because the whole point is that it is not made of anything. But what does it mean for something to exist with no spatial extent? Classical physics has no answer. You cannot have a point mass or a point charge in classical mechanics without running into infinities and contradictions. Quantum field theory gives you a framework where the electron is a quantum of the electron field, a ripple in a field that pervades all of space. The field is real, the electron is an excitation in that field. But even that description does not fully resolve the weirdness. The field is not made of anything. It is a fundamental ingredient of reality, one of several fields that together make up the standard model. The electron field is there, always, everywhere, and the particle we call an electron is what you get when you add energy to the field in just the right way. One of the strangest implications of treating the electron as a field excitation is that all electrons are identical, not just similar, identical, indistinguishable, If you swap two electrons in a quantum system, the wave function might pick up a phase, but the physics does not change. You cannot tell which electron is which, because there is no which. They are not individual objects in the way baseballs are individual objects. They are excitations in the same field. There is only one electron field, and every electron is a localized disturbance in that field. That sameness is what makes quantum statistics work. Electrons obey Fermi-Dirac statistics, a set of rules that apply to particles with half-integer spin. The rules say that no two electrons can occupy the same quantum state, a principle known as the Pauli exclusion principle. That principle is responsible for the structure of the periodic table, the stability of matter, the fact that you cannot push two solid objects through each other. If electrons were not identical, if they had internal labels or hidden properties that distinguished one from another, the statistics would be different. Chemistry would not work, matter would not be stable, the universe would be a very different place. John Wheeler, a physicist who spent much of his career thinking about quantum mechanics and general relativity, once proposed a thought experiment called the one-electron universe. The idea was that maybe there is only one electron in the entire universe, and it is moving backward and forward in time, appearing in many places at once. When the electron moves forward in time, we see it as an electron. When it moves backward in time, we see it as a positron, the electron's antiparticle. The reason every electron looks the same is because they are all the same electron, just at different moments in its timeline. Wheeler was not entirely serious. He knew the idea had problems. For one thing, there are far more electrons in the universe than positrons, so the forward and backward trips do not balance. For another, the timeline would have to weave through every point in space and time where an electron has ever existed, creating an impossibly complicated path. But the thought experiment captures something real about the electron's identity, or rather, its lack of identity. Electrons do not have serial numbers. They do not have histories you can trace. They are interchangeable, and that interchangeability is a fundamental feature of quantum mechanics. Another feature that distinguishes the electron from composite particles is its stability. Protons, despite being composite, are extraordinarily stable. The current lower limit on the proton's lifetime is something like 10 to the 34 years, far longer than the age of the universe. Nobody has ever seen a proton decay, but the proton is made of quarks, and in some theories beyond the standard model, there are processes that could in principle allow a proton to decay into lighter particles. The electron, by contrast, is absolutely stable as far as anyone can tell. It cannot decay because there is nothing lighter for it to decay into that conserves charge. The electron has the smallest mass of any charged particle. If it decayed, the products would have to include at least one charged particle, and there are no charged particles lighter than the electron, so it has nowhere to go. It just sits there forever. Every electron that has ever existed is still around, somewhere. The electrons in your body have been cycling through the universe for billions of years. Some of them were forged in the cores of stars. Some of them were floating in interstellar gas clouds. Some of them were part of the primordial hydrogen that formed in the first few minutes after the Big Bang. And they are still the same electrons, unchanged, because electrons do not age. They do not wear out. They are as fundamental as time allows. The standard model treats the electron as point-like, but it does not explain why. It does not tell you why leptons exist, or why there are 3 generations of them, or why the electron has the mass and charge it does. Those are inputs, not predictions. And that incompleteness is one of the reasons physicists suspect the standard model is not the final theory. There has to be something deeper. Maybe the electron is not truly fundamental. Maybe it is made of smaller particles called preons, and we just have not been able to probe the energy scales where preon structure becomes visible. Preon theories have been proposed, but none of them have made testable predictions, and there is no experimental evidence for them. The electron still looks like a point. Maybe the electron's properties come from interactions with fields we have not discovered yet, fields that exist at energy scales far beyond what current accelerators can reach. That is possible. The Standard Model only describes physics up to energies of a few trillion electron volts. Beyond that, we are guessing. String theory suggests that all particles, including the electron, are actually tiny vibrating strings, and the different vibration modes correspond to different particles. In that picture, the electron is not a point. It is a string with a length on the order of the Planck length, about 10 to the negative 35 meters. That is 20 trillion times smaller than the current experimental limit on the electron's size. We are nowhere close to being able to test that idea directly. What we do know is that the electron behaves as a point particle down to the smallest scales we can measure, and that behavior is consistent with it being a fundamental excitation in the electron field. The field itself is one of the building blocks of the Standard Model. It is not made of anything more basic. It is just there, woven into the fabric of space-time, and the electron is what you get when you add a quantum of energy to that field in the right way. The electron has charge, mass, and spin, and those properties are intrinsic to the field, not derived from substructure. The electron participates in electromagnetic interactions because its field is coupled to the photon field. It participates in weak interactions because its field is coupled to the W and Z boson fields. It does not participate in strong interactions because its field is not coupled to the gluon field. All of this is described by the Standard Model with extraordinary precision. The theory works. It predicts the outcomes of particle collisions, the rates of radioactive decays, the strengths of forces, the lifetimes of unstable particles. Every prediction that can be tested has been tested, and the theory passes. The electron is a central part of that success. Without the electron, there is no electromagnetism as we know it, no atoms, no chemistry, no biology. The electron is not just a particle. It is a cornerstone of the structure of reality, but it is also a mystery, a point with no size, no parts, no internal structure, yet somehow carrying charge and mass and spin. A quantum field excitation that looks like a particle when you measure it, but spreads out like a wave when you do not. A thing that is identical to every other instance of itself, indistinguishable, interchangeable, with no individual identity. A particle that cannot decay, cannot change, cannot wear out, existing unchanged since the moment it was created billions of years ago. The more you know about the electron, the stranger it becomes. And the fact that our best theory treats it as a mathematical point rather than a physical object with extent should bother you. It bothers physicists. Not because the theory is wrong, it is not, but because it is incomplete. The electron is fundamental within the framework of the Standard Model, but the Standard Model is not the final word. It cannot be. It does not include gravity. It does not explain dark matter. It does not explain why the universe has more matter than antimatter, a question that ties directly back to the electron, because the asymmetry between matter and antimatter shows up in the properties of particles like the electron and its antiparticle, the positron. Precision measurements of the electron's properties are being used right now to search for physics beyond the Standard Model. One of the most sensitive tests involves measuring the electron's electric dipole moment. The dipole moment is a measure of how asymmetrically the charge is distributed. If the electron were a perfect sphere of charge, the dipole moment would be exactly zero. The Standard Model predicts it is very nearly zero, but not exactly. Quantum corrections from virtual particles should create a tiny asymmetry, far too small to measure with current technology. But some theories beyond the Standard Model predict much larger dipole moments. If the electron has internal structure at very short distances, or if there are new particles and forces we have not discovered yet, the dipole moment could be measurably non-zero. Experiments have been looking for it for decades. So far, nothing. The dipole moment, if it exists, is smaller than about 10 to the negative 31 electron centimeters. That is an absurdly small number, and it sets tight constraints on any theory that predicts new physics. The fact that the electron's charge is distributed so symmetrically is another piece of evidence that it really is point-like and structureless down to the smallest scales we can probe. But it is also a clue. The electron's properties, its stability, its symmetry, its interactions, all of them point toward a deeper layer of physics that we have not uncovered yet. The electron is not the end of the story. It is a piece of the story, a very important piece, but there is more underneath. So what is the electron really? The honest answer is that we do not know. We know what it does, we know how it behaves, we know how to calculate its interactions with photons and other particles to extraordinary precision. We know it is fundamental within the Standard Model, meaning it has no known substructure. We know it is stable, indivisible, indistinguishable from every other electron, and essential to the existence of matter as we understand it. But we do not know what it is in any deeper sense. We do not know why it has the mass it does, or the charge it does, or why it exists at all. We do not know if it is truly a point, or if there is structure below the scales we can currently measure. We do not know if the electron field is the most fundamental thing, or if it emerges from something even more basic. These are open questions. They are the kind of questions that drive physics forward. And the electron, for all its simplicity, for all its apparent pointness, sits at the center of those questions. It is the simplest charged particle, the lightest charged particle, the most precisely measured particle. And it is still, after more than a century of study, one of the most mysterious objects in the universe. Not because we do not understand it, we understand it incredibly well, but because the more precisely we measure it, the clearer it becomes that the electron is not just a particle. It is a doorway, a clue, a piece of a puzzle that is far larger than anyone expected. And the precision with which we have measured the electron's properties, the extraordinary agreement between theory and experiment, is not just a triumph of physics, it is an invitation to look deeper, to probe smaller scales, to ask harder questions. The electron is a point particle as far as we can tell, but the universe has a way of hiding deeper layers underneath the things that look simplest. And the electron, simple as it seems, is no exception. The next step is not to ask what the electron is made of. It is to ask what the electron does when you take quantum mechanics seriously at the level of fields and forces. To ask how the electron interacts with light, with itself, with the vacuum. To build a theory that treats particles and forces on equal footing, where the electron is not just a charge sitting in space, but a dynamic player in a constantly shifting quantum field. That theory exists. It is called quantum electrodynamics, and it is the most accurate scientific theory ever tested. It takes the electron, point-like and structureless, and uses it to predict phenomena with a precision that borders on the absurd. And in doing so, it shows that even if we do not know what the electron is in some ultimate metaphysical sense, we know exactly how it behaves, down to the 11th decimal place. The electron is a point particle. We established that. No internal structure, no moving parts, no size that we can measure. It is an excitation in the electron field, a ripple in one of the fundamental fields that make up reality. That description works. It explains stability. It explains why atoms do not collapse. It explains the shapes of orbitals, the structure of the periodic table, the behavior of matter at the smallest scales we can probe. But it raises a new question. If the electron is a quantum object living in a field, and if light is also a quantum object living in a different field, how do the two interact? How does an electron emit a photon? How does it absorb one? How does the electromagnetic force actually work when you take quantum mechanics seriously? Classical electromagnetism had an answer. A charged particle creates an electric field around it. Another charged particle feels that field and responds to it. The field is continuous, smooth, extending through all of space. Change the position of one charge and the field ripples outward at the speed of light, eventually reaching the other charge and altering its motion. It was a beautiful picture. Maxwell's equations described the field with extraordinary precision. They explained light, radio waves, the behavior of circuits and magnets, everything electromagnetic. And they worked perfectly as long as you did not look too closely at what was happening inside atoms. When you zoomed in to quantum scales, the classical picture broke. The electron should radiate continuously as it orbited the nucleus. It did not. The electron should spiral into the nucleus in a fraction of a nanosecond. It did not. The field description was incomplete. It needed to be quantized. That process, turning classical field theory into quantum field theory, took decades. It was messy, frustrating, and littered with infinities that no one knew how to handle. But by the late 1940s, a handful of physicists had figured it out. They built a new framework, a theory that treated both matter and light as quantum fields, where particles were excitations in those fields and forces were carried by the exchange of other particles. The theory they built is called quantum electrodynamics, QED for short, and it is the most accurate scientific theory ever tested. Not approximately accurate, not close. Accurate to the point where the predictions match experimental measurements to better than 1 part in a trillion. That level of precision is absurd. It is the equivalent of predicting the distance from New York to Los Angeles to within the width of a human hair, and QED does it routinely. The foundation of QED is quantum field theory, a framework that extends quantum mechanics to systems with an indefinite number of particles. In ordinary quantum mechanics, you start with a fixed number of particles, say 1 electron, and you describe it with a wave function. The wave function evolves according to Schrödinger's equation, and measurements give you probabilities for where the electron might be. That works fine for atoms and simple systems where the number of particles does not change, but it breaks down when particles can be created or destroyed. And in the real world, particles are created and destroyed all the time. An electron can emit a photon. A photon can split into an electron and a positron. Particles pop in and out of existence as virtual fluctuations in the vacuum. You cannot describe that with ordinary quantum mechanics because the wave function assumes a fixed particle number. You need a framework where the fields themselves are the fundamental objects, and particles are just temporary excitations in those fields. Quantum field theory gives you that. Instead of saying, there is 1 electron described by a wave function, you say there is an electron field that pervades all of space. The field has a value at every point, and that value is not a number. It is an operator, a mathematical object that can create or destroy particles when it acts on the quantum state of the system. Add energy to the electron field in the right way, and you create an electron. Remove energy, and the electron disappears. The field is always there. The particles come and go. This is not just a mathematical trick. It is the correct description of what particles are. An electron is not a little ball moving through space. It is a localized disturbance in the electron field. A photon is not a little packet of light. It is a quantum of the electromagnetic field. Both fields exist everywhere, and what we call particles are ripples in those fields, excitations that carry energy and momentum and can interact with each other. The interactions are the key part. In QED, forces are not mediated by continuous fields in the classical sense. They are mediated by the exchange of photons. Here is how it works. Two electrons repel each other because they both have negative charge. In the classical picture, one electron creates an electric field, and the other electron feels that field and experiences a force pushing it away. In QED, the process is different. One electron emits a virtual photon. That photon travels to the second electron, which absorbs it. The emission and absorption transfer momentum between the two electrons, and that momentum transfer is what we perceive as the electromagnetic force. The photon is called virtual because it exists only for the duration of the interaction. It is not a real photon that you could detect with a camera or a light sensor. It is a quantum fluctuation, a temporary disturbance in the electromagnetic field that pops into existence just long enough to carry the force and then disappears. This sounds bizarre, and it is, but it is also how quantum mechanics works when you apply it to fields. The uncertainty principle says that energy and time are paired variables. The more precisely you try to define the moment when a process happens, the less precisely you can define the energy involved. That means short-lived processes can violate energy conservation temporarily. A virtual photon can carry more or less energy than it would need to be a real photon, as long as it disappears quickly enough that the violation stays within the limits set by the uncertainty principle. The shorter the time, the larger the allowed energy fluctuation. Virtual particles are constantly popping in and out of existence everywhere in space, borrowing energy from the vacuum and paying it back before anyone can catch them cheating. The vacuum is not empty. It is seething with virtual particles, a roiling quantum foam that underpins every interaction in the universe. Richard Feynman developed a way to visualize these interactions that became the standard language of particle physics. He called them diagrams, and they are now named after him. A Feynman diagram is a simple picture showing how particles interact over time. Time runs from left to right or bottom to top, depending on how you draw it. Particles are represented by lines. Straight lines are electrons or positrons. Wavy lines are photons. The lines meet at points called vertices, where interactions happen. An electron emits or absorbs a photon at a vertex. An electron and a positron annihilate at a vertex, producing a photon. A photon splits into an electron-positron pair at a vertex. Each diagram corresponds to a specific mathematical expression, and you calculate the probability of the process by working out the math associated with the diagram. The simplest diagram for the electromagnetic force between two electrons shows two electron lines coming in from the left, a wavy photon line connecting them in the middle, and two electron lines going out to the right. One electron emits the photon. The other absorbs it. The photon carries momentum from one to the other. That momentum transfer is the force. The diagram is not just a picture, it is a calculation tool. You plug in the energies and momenta of the incoming and outgoing particles, follow the rules Feynman laid out for translating diagrams into integrals, and you get a number. That number is the probability amplitude for the process. Square it, and you get the actual probability. Add up all possible diagrams for a given interaction, and you get the total probability. The more complicated the diagram, the smaller its contribution. But in principle, you have to sum over every possible way the interaction could happen, including diagrams with loops, where virtual particles are created and then annihilate, and diagrams with multiple photon exchanges. The sum is infinite, which sounds like a disaster, but it turns out the infinite series converges, at least for electromagnetism, and you can calculate the result to arbitrary precision by including more and more terms. Feynman was not the only one working on this. Julian Schwinger at Harvard and Shinichiro Tominaga in Japan independently developed their own versions of QED in the late 1940s. Schwinger's approach was more formal, rooted in operator methods and field equations. Tominaga's work emphasized covariance, making sure the theory respected the principles of special relativity. Feynman's diagrams were more intuitive, easier to visualize, and easier to calculate with. All three approaches gave the same answers. Freeman Dyson, a young mathematician at the Institute for Advanced Study, proved in 1949 that the three formulations were mathematically equivalent, different ways of saying the same thing. The three main developers, Feynman, Schwinger, and Tominaga, shared the Nobel Prize in Physics in 1965. Dyson, who did not develop the theory but showed how the pieces fit together, did not get the prize. The Nobel Committee does not award more than 3 people for a single prize, and Dyson was left out. It is one of the more glaring omissions in the history of the award. The development of QED was not smooth. The theory kept producing infinities, not just mathematical infinities that you could ignore. Physical infinities. When you calculated the energy of the electron's electromagnetic field, integrating over all of space, the result was infinite. When you calculated the corrections to the electron's mass from its interactions with virtual photons, the result was infinite. When you calculated the correction to the electron's charge, also infinite. Classical electromagnetism had the same problem. A point charge produces an electric field that diverges at the location of the charge, and the energy in that field is infinite. But in classical physics, you could hand-wave the problem away by saying the electron was not really a point. It was a tiny sphere with a very small radius, and if you cut off the integration at that radius, the energy came out finite. That trick does not work in quantum field theory because the electron really is a point, and cutting off the integration arbitrarily breaks the mathematical structure of the theory. The solution is a process called renormalization. Renormalization is not a trick. It is a systematic procedure for absorbing the infinities into the definitions of the parameters you start with. Here is the idea. The electron has a bare mass and a bare charge, the values it would have if it existed in perfect isolation with no interactions. But the electron does not exist in isolation. It is constantly interacting with the electromagnetic field, emitting and absorbing virtual photons, surrounded by a cloud of virtual particle-antiparticle pairs that pop in and out of existence. Those interactions modify the electron's properties. The mass you measure in the lab is not the bare mass. It is the bare mass plus all the corrections from the virtual interactions. Same with the charge. The charge you measure is the bare charge plus corrections. The bare quantities are not observable. They are just parameters in the equations. What you actually measure are the renormalized quantities, the mass and charge dressed by the cloud of virtual particles. Renormalization says that you should not try to calculate the bare mass and bare charge. You should take the measured mass and charge as inputs and use them to predict other things. The infinities in the bare quantities get absorbed into those inputs, and everything else you calculate comes out finite. As long as you only need to renormalize a finite number of parameters, the theory is predictive. You measure a few quantities, plug them in, and the theory tells you everything else. QED is renormalizable. You renormalize the electron's mass, the electron's charge, and one more parameter related to how the fields are defined. After that, every other prediction is finite and calculable. The procedure works. It has been tested thousands of times, but it still feels like sleight of hand. You are moving the infinities around rather than getting rid of them. Physicists in the 1940s and 50s were deeply uncomfortable with renormalization. Dirac hated it. He thought it was a sign that QED was fundamentally flawed and needed to be replaced with a better theory. Feynman admitted in his Nobel lecture that he found the procedure unsatisfying, even though it worked. But no one has found a better way. And the predictions that come out of renormalized QED are so accurate that the discomfort has faded into background noise. The theory works, and that is what matters. The most famous test of QED is the electron's magnetic moment. Every charged particle with spin has a magnetic moment, a measure of how it behaves in a magnetic field. Dirac's equation, the relativistic version of the Schrödinger equation, predicts a specific value for the electron's magnetic moment based on its charge, mass, and spin. That value is called the Dirac magnetic moment, but the actual measured magnetic moment is slightly different. The difference is tiny, about 0.1%, but it is real and measurable. The deviation is called the anomalous magnetic moment, and it comes from quantum corrections. The electron interacts with virtual photons, and those interactions shift the magnetic moment slightly. The first correction, calculated by Schrödinger in 1947, comes from a single virtual photon being emitted and reabsorbed by the electron. The diagram is a loop, and the calculation involves an integral over all possible momenta the virtual photon could have. The result is a correction proportional to the fine structure constant, a dimensionless number that measures the strength of the electromagnetic force. The fine structure constant is about 1 divided by 137, so the correction is small, but it is measurable. Schrödinger's prediction matched the experimental data available at the time, and it was one of the first major successes of QED. Since then, the calculation has been extended to higher and higher orders. The second-order correction includes diagrams with two virtual photons, or a virtual photon splitting into a virtual electron-positron pair. The third order includes even more complicated processes. Calculating the anomalous magnetic moment to high precision requires summing thousands of Feynman diagrams, each one representing a different way virtual particles can interact with the electron. The most recent calculations go to 10th order, involving diagrams with 10 or more vertices. The integrals are horrendously complicated. Many of them cannot be done analytically and require numerical methods. The calculation has taken decades of work by multiple research groups, and the result is a theoretical prediction that matches the experimental measurement to better than 1 part in 10 billion. Some sources say the agreement is to 9 significant figures. Others say parts per trillion. The exact number depends on which measurement and which year you are talking about, but the point is the same. QED predicts the electron's magnetic moment with a precision that is almost incomprehensible. The muon, the heavier cousin of the electron, provides another test. The muon has the same charge and spin as the electron, but it is about 200 times more massive. Its anomalous magnetic moment has been measured to extraordinary precision at Brookhaven National Laboratory and more recently at Fermilab. The theoretical prediction, calculated using QED plus small contributions from the weak and strong nuclear forces, matches the measurement to about 1 part in 10 million. There is a small discrepancy, a few parts per million, that has been the subject of intense debate. If the discrepancy is real, it could be a sign of new physics beyond the standard model. If it is not, it is a sign that the calculation or the measurement has subtle errors. As of the most recent results, the jury is still out. But the fact that we can calculate and measure the muon's magnetic moment to that level of precision is itself a triumph. QED also explains the Lamb shift, a tiny difference in energy between two quantum states of the hydrogen atom that should have the same energy according to Dirac's equation. The two states, called the 2s1/2 and the 2p1/2 states, differ in their orbital angular momentum but have the same principal quantum number and spin. Dirac's equation says they should be degenerate, meaning they have exactly the same energy. But high-precision measurements by Willis Lamb in 1947 showed they were not. The 2s state has slightly higher energy, by about 1 part in a million. The shift is caused by the interaction between the electron and virtual photons. The electron in the 2s state spends more time close to the nucleus, where the electromagnetic field is stronger, and it interacts more strongly with the vacuum fluctuations. The calculation is complex, involving integrals over all possible wavelengths of virtual photons, but QED predicts the shift accurately. Lamb won the Nobel Prize in Physics in 1955 for measuring it. Feynman called QED the jewel of physics. He was not exaggerating. The theory does not just work. It works with a level of precision that borders on the unbelievable. You can calculate the probability of an electron scattering off another electron. You can calculate the rate at which an excited atom emits a photon. You can calculate the energy levels of hydrogen to 15 decimal places. Every prediction that can be tested has been tested, and the theory passes every time. QED is not approximate. It is not a rough guide. It is exact, within the limits set by the uncertainty principle and the precision of the measurements. That makes it the most successful scientific theory in history. Not the most important, necessarily. General relativity explains gravity, and gravity shapes the universe on large scales. Quantum mechanics explains atomic structure, and atomic structure is the foundation of chemistry and biology. But QED is the most accurate, the most precisely tested. The theory that comes closest to capturing a piece of reality exactly as it is. There is one place where QED spectacularly fails, and it is worth mentioning because the failure is so extreme it is almost funny. QED predicts that the vacuum has energy. The zero-point energy of the electromagnetic field, calculated by summing over all possible modes of oscillation, is infinite. You can renormalize that infinity away by redefining what you mean by zero energy, setting the vacuum energy to zero by hand. But if you try to calculate the actual energy density of the vacuum using QED, and you cut off the integral at the Planck scale, the smallest scale where quantum field theory is expected to be valid, you get a number that is about 10 to the power of 120 times larger than the observed energy density of the universe. That is not a typo. 120 orders of magnitude. It is the worst prediction in the history of physics. The vacuum energy problem, also called the cosmological constant problem, is one of the deepest unsolved mysteries in theoretical physics. QED works perfectly for calculating particle interactions, but it says nothing useful about the energy of empty space. That is a problem for quantum gravity, not QED, and quantum gravity does not exist yet as a consistent theory. So the vacuum energy discrepancy sits there, unresolved, a glaring reminder that even the most accurate theory we have is incomplete. But that incompleteness does not diminish what QED accomplishes. It describes the interaction of light and matter with a precision unmatched by any other theory. It explains why atoms are stable, why electrons do not radiate when they sit in stationary states, why they do radiate when they transition between states. It explains the fine structure of spectral lines, the tiny splittings caused by relativistic corrections and spin-orbit coupling. It explains pair production, the process where a photon with enough energy can create an electron-positron pair out of nothing. It explains annihilation, the reverse process where an electron and positron collide and convert their mass into photons. It explains Compton scattering, where a photon bounces off an electron and loses energy. It explains the photoelectric effect, the process Einstein used to argue that light is made of particles. Every electromagnetic process, from the bending of light around a massive object to the glow of a neon sign, is described by QED. The theory also gives you a framework for understanding what forces are at the quantum level. Forces are not mysterious pulls or pushes transmitted through space. They are the exchange of particles. The electromagnetic force is mediated by photons. The strong nuclear force, which holds quarks together inside protons and neutrons, is mediated by gluons. The weak nuclear force, which causes radioactive decay, is mediated by W and Z bosons. All three forces are described by quantum field theories that are extensions of QED. The strong force is described by quantum chromodynamics, QCD. The weak force is described by the electroweak theory, which unifies electromagnetism and the weak force into a single framework. Together, QED, QCD, and the electroweak theory make up the standard model of particle physics, and all of them are built on the same foundation QED established. Particles are excitations in fields. Forces are mediated by the exchange of other particles. Interactions are calculated using Feynman diagrams. Infinities are absorbed through renormalization. The framework works. It has been tested at particle accelerators around the world for decades, and it has passed every test. QED is a triumph not just of physics, but of human reasoning. It is a theory built on layers of abstraction. Quantum mechanics, which says particles are waves. Special relativity, which says space and time are unified. Field theory, which says particles are excitations in fields. Renormalization, which says infinities can be tamed by redefining what you measure. None of those ideas are intuitive. None of them match the way the world looks at human scales. But when you put them together and apply them consistently, you get a theory that predicts the behavior of electrons and photons to better than 1 part in a trillion. That is not luck. That is understanding. Deep, precise, mathematical understanding of how a piece of the universe works. The electron's magnetic moment, calculated to 10 significant figures and matching experiment to within the width of a hair, is proof that quantum field theory is not just a useful approximation. It is the correct description of reality at the scales where particles and forces meet. The electron is a point particle with no internal structure. It interacts with the electromagnetic field by emitting and absorbing photons. Those interactions, calculated using QED, produce tiny corrections to the electron's properties. The corrections are measurable, the predictions match, the theory works. And that match, that extraordinary agreement between theory and experiment, is one of the great achievements of 20th century science. It is the reason physicists trust quantum mechanics, even when it produces results that seem absurd. It is the reason we know that particles are not little balls. that forces are not continuous fields, that the vacuum is not empty. QED tells us what the world is really like at the smallest scales we can probe, and it does so with a level of confidence that no other theory can match. The electron holds together because quantum mechanics says it cannot collapse. Quantum electrodynamics tells you why. The electron sits in a quantum state where the electromagnetic force pulling it toward the nucleus is balanced by the uncertainty principle pushing it outward. It does not radiate because it is not accelerating in the classical sense. It is sitting in a stationary state, a stable configuration of the electron field, and when it does transition to another state, emitting or absorbing a photon, the process is governed by the rules of QED. The photon is real, the transition is quantized, the energy is exact. The atom is stable because the rules of quantum field theory make it stable. And those rules, tested to 10 significant figures, are as close to a final answer as physics has ever come. QED is not just a theory, it is a monument. A testament to what happens when you take the strange implications of quantum mechanics seriously, when you refuse to settle for approximations, when you demand that your predictions match reality down to the last decimal place. The theory works. It works better than any theory has a right to. And it works because the electron, point-like and structureless as it is, really does behave exactly the way the equations say it should. The universe is quantum, the electron is the proof, and QED is the manual. The electron sits in its quantum state. It does not move in the way we think of movement. It does not orbit in the way planets orbit. It exists as a cloud of probability, a wave function spread over space, held in place by rules that took humanity a century to write down. And because it sits there, stable, unchanging, governed by the uncertainty principle and the exclusion principle and the equations of quantum mechanics, you exist, your body exists, the chair you are sitting on exists, the planet beneath you exists, the stars burning hydrogen in the night sky exist. Everything that has structure, everything that has chemistry, everything that can think or grow or change, all of it traces back to a single fact. The electron does not collapse into the nucleus. That is the foundation, not a footnote, not a detail you can skip over on your way to more exciting topics. The foundation. If the electron collapsed, atoms would not be stable. If atoms were not stable, molecules could not form. If molecules could not form, there would be no water, no carbon chains, no proteins, no DNA, no cells, no organisms, no brains, no thoughts. The universe would be a thin soup of free protons and free electrons drifting through an expanding void, incapable of assembling into anything more complex than a gas cloud. And those gas clouds would not even condense into stars, because stars require stable hydrogen, and hydrogen is an atom, one proton and one electron, and if the electron cannot stay bound to the proton, there is no hydrogen, there is nothing, just particles scattering through darkness forever. We came very close to living in that universe, or rather, we came very close to realizing we should not exist in this one. In the early 1900s, the best minds in physics looked at the atom and concluded it was impossible. The equations said so. Maxwell's electromagnetism, one of the towering achievements of 19th century science, predicted that any charged particle moving in a circle would radiate energy continuously. The electron orbiting the nucleus was moving in a circle, therefore it should radiate. As it radiated, it should lose energy. As it lost energy, it should spiral inward. The collapse should take less than a nanosecond. The atom should not exist. And yet there you were, made of atoms, holding instruments made of atoms, living on a planet made of atoms, staring at experimental data that very clearly showed atoms were not collapsing. The contradiction was not subtle, it was existential. The theory said reality was impossible. Reality disagreed. Quantum mechanics resolved the contradiction by changing the rules. The electron was not a particle on a trajectory. It was a wave, or a cloud, or a solution to an equation that described where it might be if you looked. The act of looking, of measuring, forced it to pick a location, but before the measurement, it did not have one. It existed in a superposition of possible positions, and the shape of that superposition was determined by Schrödinger's equation. The allowed states, the orbitals, were standing waves, stable configurations where the wave function connected smoothly with itself and did not destructively interfere. Those states did not radiate, they just sat there, unchanging, as long as you left them alone. The electron in the ground state of hydrogen occupied the lowest energy level, and there was nowhere lower for it to go. It could not collapse because quantum mechanics did not allow it. The uncertainty principle, the rule that said you could not pin down both position and momentum exactly, created a minimum kinetic energy that prevented the electron from ever sitting still at the nucleus. The quantum fuzz, the unavoidable jitter built into the fabric of reality, was what held the atom together. That realization did not just save the atom, it explained chemistry. The periodic table, that grid of elements organized into rows and columns, is a direct map of how electron orbitals fill up as you add more protons to the nucleus and more electrons to balance the charge. Each element has a unique electron configuration, a specific arrangement of occupied orbitals, and that configuration determines everything about how the element behaves. Hydrogen has one electron in the 1s orbital. It wants to grab another electron to fill the shell, which is why it forms bonds so readily. Helium has 2 electrons in the 1s orbital, completely filling the first shell. It does not want to bond with anything because it is already full. That is why helium is inert. Carbon has 6 electrons, 2 in the 1s orbital and 4 in the second shell, with 2 in the 2s orbital and 2 in the 2p orbitals. The 2p electrons are unpaired, and carbon can share them with other atoms, forming up to 4 bonds. That ability to form 4 bonds is why carbon is the backbone of organic chemistry. It can link to itself, to oxygen, to nitrogen, to hydrogen, building chains and rings and branching structures of arbitrary complexity. DNA is a carbon chain. Proteins are carbon chains. The molecules that make you alive are all built on a carbon scaffold, and carbon works because of the way its electron orbitals are shaped and filled. Schrödinger's equation determines those shapes. The Pauli exclusion principle determines how they fill. Together, they explain why water is a liquid, why oxygen is a gas, why iron is magnetic, why sodium explodes when you drop it in water. All of chemistry, the entire science of how substances interact and transform, comes down to the behavior of electrons in atoms. And the behavior of electrons in atoms comes down to quantum mechanics. Biology is built on chemistry. You are a collection of chemical reactions, thousands of them happening simultaneously in every cell of your body. Enzymes catalyzing the breakdown of sugars, DNA polymerase copying your genetic code, hemoglobin shuttling oxygen through your bloodstream, neurons firing electrical signals across synapses. Every one of those processes depends on molecules with specific shapes, and those shapes come from the way electron orbitals overlap and bond. A protein folds into a particular 3-dimensional structure because the amino acids that make it up have electron clouds that repel or attract each other in precise ways. Change the shape of a protein and you change its function. Sometimes you break it entirely. Sickle cell anemia is caused by a single amino acid substitution in the hemoglobin protein. One amino acid out of hundreds swapped for a different one, and the protein folds differently. The new shape causes red blood cells to deform, clogging blood vessels and starving tissues of oxygen. One mutation, one change in the electron configuration of a single molecular bond, and the whole system breaks. That is how sensitive biology is to the quantum rules underneath. Those rules do not just apply to life, they apply to everything. Stars burn because quantum mechanics allows fusion. Hydrogen nuclei, protons, repel each other because they are both positively charged. In classical physics, you would need enormous energies to overcome that repulsion and bring the protons close enough to fuse. The core of the Sun is hot, about 15 million degrees Celsius, but that is not hot enough. Classical physics says fusion should not happen at the temperatures and pressures inside a star. Quantum mechanics says it can, because particles can tunnel through energy barriers they do not have enough energy to climb over. The protons do not need to overcome the repulsion entirely. They just need to get close enough that the strong nuclear force, which operates at very short ranges, can pull them together. Quantum tunneling makes that possible. A small fraction of protons, the ones in the high-energy tail of the velocity distribution, tunnel through the electromagnetic barrier and fuse, releasing energy. That energy heats the star, which keeps the pressure up, which keeps the fusion going. The process is self-sustaining. Stars burn for billions of years, and they burn because quantum mechanics lets particles do things classical physics forbids. Everything you see in the night sky, every star, every galaxy, every nebula glowing with ionized gas, exists because quantum mechanics works. Hydrogen, the most abundant element in the universe, is stable because the electron and proton bind into an atom that does not collapse. Those hydrogen atoms clump together under gravity, forming clouds, and the clouds collapse into stars. Inside the stars, hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon and oxygen fuse into heavier elements like magnesium, silicon, iron. When a massive star runs out of fuel, it explodes in a supernova, scattering those heavy elements into space. New clouds form, enriched with carbon, nitrogen, oxygen, all the elements you need to build planets and life. The Sun is a second or third generation star, born from a cloud that contained the debris of earlier stars. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was forged in stars that died billions of years ago. And the process that made it, the chain of fusion reactions that built the periodic table one element at a time, only works because quantum mechanics lets particles tunnel, lets energy levels quantize, lets atoms stay stable long enough to interact and bond and build. The universe is not classical, it never was. The classical picture, particles with definite positions moving on definite trajectories, obeying Newton's laws and Maxwell's equations, is an approximation. It works at human scales, where Planck's constant is so small that quantum effects average out and disappear. But zoom in far enough, look closely enough, and the approximation breaks. Particles do not have definite positions until you measure them. They do not have definite momenta. They do not follow paths. They exist as probability clouds, wave functions that evolve according to quantum rules, and only collapse into definite states when you force them to, by interacting with them. That weirdness, that departure from common sense, is not a bug, it is the operating system. The universe runs on quantum mechanics, and because it does, atoms are stable, chemistry works, stars burn, life evolves, You are here. The precision with which we understand this is staggering. Quantum electrodynamics predicts the electron's magnetic moment to better than 1 part in 10 billion. That is 10 significant figures. The theoretical prediction and the experimental measurement agree to within the width of a hair if you scaled the measurement up to the distance from New York to Los Angeles. That level of accuracy is not just impressive, it is a statement about the nature of reality. The electron is not approximately a point particle, it is a point particle as far as we can measure. It does not approximately obey the equations of QED, it obeys them exactly within the limits of the uncertainty principle. The theory is not a rough guide, it is the correct description of how electrons and photons interact. And because we know that, because we have tested it to absurd precision, we can say with confidence that the quantum mechanical picture of the atom is not just a useful model, it is the way the atom actually is. That confidence has consequences. Every piece of technology you interact with, every device you use, rests on quantum mechanics. The computer you are using to watch this, the smartphone in your pocket, the LED lights in your room, all of them exploit quantum effects. Transistors, the building blocks of modern electronics, are switches that control the flow of electrons through a semiconductor. The behavior of electrons in semiconductors, the way they jump between energy levels, the way they tunnel through barriers, all of it is quantum. The screen you are looking at emits light because electrons in the display material are excited to higher energy states and then drop back down, releasing photons. The colors you see correspond to the energy differences between quantum states. The GPS satellite triangulating your position uses atomic clocks, and atomic clocks work because the transition frequency between two energy levels in a cesium atom is extraordinarily stable. That frequency is a quantum property set by the difference in energy between the hyperfine states of the cesium ground state. The entire infrastructure of the modern world, the communication networks, the power grids, the medical imaging devices, the lasers, the superconductors, all of it is built on our understanding of quantum mechanics. None of it would work if the theory were wrong, and yet the theory is incomplete. We know that. Quantum mechanics explains atoms, molecules, chemistry, electromagnetism, the behavior of particles at energies up to a few trillion electron volts. It does not explain gravity. General relativity explains gravity. The two theories, quantum mechanics and general relativity, are both extraordinarily successful in their own domains, but they are not compatible. They give different answers when you try to describe the same situation, and neither one reduces to the other in any obvious way. At the scale of atoms, gravity is so weak you can ignore it. At the scale of planets and stars, quantum effects are so small you can ignore them. But there are places where both matter, and we do not have a theory that works there. The center of a black hole, where general relativity says the curvature of space-time becomes infinite, and quantum mechanics says that cannot be right. The first moments after the Big Bang, when the entire observable universe was smaller than an atom, and both quantum effects and gravitational effects were enormous. We do not know what happens in those regimes. Quantum gravity, the theory that would unify quantum mechanics and general relativity, does not exist yet. String theory is one candidate. Loop quantum gravity is another. Neither one is testable with current technology, and neither one has made a prediction that we can go out and check, so we wait. We build better accelerators. We look for hints in the cosmic microwave background, in the rotation curves of galaxies, in the gravitational waves produced by colliding black holes. We hope that somewhere in the data there is a clue. The electron sits at the center of that search. Not because the electron is mysterious. It is not. We understand the electron extraordinarily well, but because the electron is simple, it is the simplest charged particle, the lightest charged particle, the most precisely measured particle. If there is new physics hiding at higher energies, if the standard model is incomplete in some way we have not detected yet, the electron might be the place where we find it. Physicists are measuring the electron's properties to higher and higher precision, looking for deviations from the predictions of QED. The electron's electric dipole moment, a measure of how asymmetrically its charge is distributed, should be very nearly zero according to the standard model. If it is measurably non-zero, that would be a sign of new physics, new particles, new forces we have not discovered yet. So far, nothing. The dipole moment, if it exists, is smaller than 10 to the negative 31 electron centimeters. That is an absurdly small number, and it sets tight constraints on any theory that predicts something larger. The electron is not giving up its secrets easily. There is also the fine structure constant, the dimensionless number that measures the strength of the electromagnetic force. It is about 1 divided by 137, and nobody knows why. It is one of the fundamental constants of nature, a pure number with no units, and it shows up everywhere in physics. The fine structure constant determines how strongly electrons and photons interact. It sets the scale of atomic energies. It controls the rate at which atoms emit light, and it appears to be finely tuned. If the fine structure constant were much larger, atoms would not be stable. Electrons would be pulled too tightly to nuclei, and the orbitals would overlap in ways that disrupted chemistry. If it were much smaller, atoms would be too large, bonds would be too weak, and molecules would not hold together. The range where chemistry works, where complex molecules can form and life can evolve, is narrow. We live in a universe where the fine structure constant happens to have a value that allows structure. That could be a coincidence, or it could be a hint that the constants of nature are not arbitrary, that they are constrained by some deeper principle we have not figured out yet. Physicists have spent decades trying to derive the value of the fine structure constant from first principles. Nobody has succeeded. It remains an input, a number you measure and plug into the equations. The same is true for the electron's mass and charge. We know what they are. We can measure them to extraordinary precision, but we do not know why they have the values they do. Why is the electron's mass about 1/2000th the mass of a proton? Why is its charge exactly equal and opposite to the charge of a proton? The standard model does not answer those questions. It takes the masses and charges as inputs and uses them to predict everything else. That is unsatisfying. It feels like the theory is incomplete, like there is a layer underneath that we are missing. Some physicists suspect the electron is not truly fundamental, that it is made of smaller particles called preons, and the mass and charge come from the way the preons are arranged. Other physicists think the electron is fundamental, but its properties emerge from interactions with fields we have not discovered yet, fields that exist at energy scales far beyond what we can currently probe. String theory suggests that all particles, including the electron, are tiny vibrating strings, and the properties of the particle depend on the vibration mode of the string. In that picture, the electron is not a point. It is a string with a length on the order of the Planck length, about 10 to the negative 35 meters. That is so small, we will never be able to measure it directly. But if string theory is correct, the electron's mass and charge are not arbitrary. They are determined by the geometry of the extra dimensions the strings vibrate in. That would be a profound answer. We do not know if it is the right answer. String theory has not made any testable predictions yet. What we do know is that the electron, simple as it is, connects to everything. Atomic stability depends on the electron. Chemistry depends on atomic stability. Biology depends on chemistry. The structure of stars depends on chemistry and quantum tunneling. The formation of planets depends on stars. The evolution of life depends on planets. The universe, in its current form, with galaxies and stars and planets and people, exists because electrons behave the way they do. Change the electron's properties, change the rules of quantum mechanics, and you get a different universe. Maybe one with no structure at all, maybe one with different kinds of structure, different chemistry, different life. We do not know. We only have one universe to look at, and in this one, the electron is stable, the fine structure constant is 1/137, and atoms hold together long enough for complicated things to happen. That fact, the fact that the universe is capable of supporting complexity, has led to a philosophical debate that has been running for decades. The constants of nature, the electron's mass, the fine structure constant, the strength of gravity, the cosmological constant, all of them appear to be finely tuned. Change any one of them by more than a small amount, and the universe becomes inhospitable to life. Some people take that as evidence of design, a sign that the universe was set up deliberately to allow observers to exist. Others take it as evidence of a multiverse, an enormous ensemble of universes with different constants, and we happen to live in one of the rare ones where the constants allow complexity. Still others think the fine-tuning is an illusion, that the constants are not independent, that they are related by some deeper principle we have not discovered yet. All three positions are philosophically contentious. None of them can be tested directly, but the empirical fact remains. The universe we live in is balanced on a knife edge. The constants that determine how particles interact, how forces work, how atoms behave, are all within the narrow range where chemistry is possible. And because chemistry is possible, you are possible. Quantum mechanics is not just a theory, it is a lens, a way of seeing the world that reveals layers most people never think about. When you look at your hand, you see skin, fingers, a solid object. Quantum mechanics says that solidity is an illusion. Your hand is mostly empty space. The nuclei of the atoms are tiny, and the electrons are probability clouds spread over regions thousands of times larger. The atoms do not touch. They repel each other electromagnetically when they get close, and that repulsion is what you feel as solidity. The sensation of touch is the feeling of electron clouds pushing against each other, mediated by the exchange of virtual photons. You are not solid. You are a pattern of quantum fields, held together by forces that operate on scales so small you cannot directly perceive them. That pattern is stable because the rules of quantum mechanics make it stable. The electron does not collapse. The orbitals fill in a predictable order. The bonds hold, and because they hold, you hold. You are a temporary arrangement of particles governed by equations written down less than a century ago. The fact that you are here, thinking, reading, processing these words, is proof that the equations are correct. You are the experiment, and the result is clear. Quantum mechanics works. The journey from Rutherford's nucleus to quantum electrodynamics took about 50 years. 50 years of confusion, false starts, bitter arguments, and occasional flashes of insight. Planck quantized energy to fix a problem with ovens. Einstein quantized light to explain the photoelectric effect. Bohr quantized the atom to stop it from collapsing. De Broglie said particles were waves. Heisenberg said you could not know everything. Schrödinger wrote down the equation. Bohr said the equation described probabilities. Feynman drew diagrams. Schwinger and Tomonaga worked out the math. Dyson showed they were all saying the same thing, And out of that mess, a theory emerged. A theory that explains why matter is stable, why chemistry works, why the universe looks the way it does. The theory has been tested thousands of times. It passes every test. It predicts the electron's magnetic moment to 10 significant figures. It explains the Lamb shift. It explains the fine structure of hydrogen. It explains pair production, annihilation, Compton scattering, every electromagnetic process ever observed. It is the most accurate scientific theory in history, and it started because someone noticed that the atom should collapse and does not. That is the lesson. The universe does not owe you an intuitive explanation. It does not care whether the answer makes sense to a brain evolved to hunt prey and avoid predators on the African savanna. The rules at quantum scales are not the rules you experience every day. Particles do not have definite positions. They do not follow paths. Measurement is not a passive act. It changes the system. The vacuum is not empty. Forces are not smooth. Reality is quantized, probabilistic, strange, and yet it works. It produces atoms, molecules, stars, planets, people. It produces complexity, structure, life. You exist because quantum mechanics is true. Not approximately true, not sort of true. True in the most rigorous sense, tested to precision that borders on the absurd, confirmed by every experiment ever designed to check it. The electron does not collapse. That is the foundation. Everything else, all of chemistry, all of biology, all of the structure you see around you, is built on that foundation. The universe is made possible by the quantum rules that govern the electron. And the fact that we figured those rules out, that we can write them down and use them to predict the behavior of particles to 10 decimal places, is one of the great achievements of human thought. We looked at the atom and saw a mystery. We kept looking until the mystery became a theory. And the theory, strange as it is, turned out to be the way the world actually works. That is science, that is physics, and that is why you are here. So here we are, 13.8 billion years after the Big Bang, sitting on a planet made of atoms that should not have lasted long enough to assemble into anything. Your body is hydrogen forged in the first 3 minutes of the universe, carbon built in the cores of dead stars, oxygen scattered across space in supernovae, all of it held together by electrons that refused to collapse when every equation said they should. The fact that you are breathing right now is not a given. It is not inevitable. It is the result of a set of quantum rules so strange, so counterintuitive, so fundamentally at odds with human intuition, that it took the smartest people alive nearly 50 years to write them down. And when they did, when they finally assembled the equations and tested them, the universe answered back with a precision that borders on the supernatural. 1 part in 10 billion, 10 significant figures. The electron's magnetic moment, predicted and measured, matching to a degree that makes every other scientific achievement look like a rough sketch. That is not luck. That is not approximation. That is